about all the ways you can use GDAL to convert files and manipulate them and reproject them and stuff. I often refer to that as a great resource of ways of converting files.
Thank you.
There are more questions. I don't know if people want to ask those.
Yeah, there's some people have been answering questions here in the Q&A. That's really helpful.
So Patrick, do you want to ask your question?
Yeah, sure. So my question is just more like high level, and we did talk about this a little bit already, but in general, like when would you choose to use TopStar instead of like strip map mode? Like, are there any applications when one is preferred over the other, or does it just depend on when whatever is available?
It's satellite data dependent, is the short answer. The Sentinel-1 interferometric wide swath data, which is what most of the world is covered by with Sentinel-1, is all in TOPS. So most of the time, if you're processing Sentinel-1, you're just using the TOPS mode data. So that's one thing. And some of the other satellites are predominantly strip map.
Yeah, all the other satellites.
Well, apart from LS2, which was also ScanSAR, which is slightly.
Oh yeah, we don't cover ScanSAR. That's another.
ScanSAR is a mode that LS2 has, where the beam kind of swings out in range in sort of sweeps.
Yeah, it's similar to TOPS, but different. So you have to use a different processor.
It doesn't go backwards and forwards, which is the key. Anything processed in strip map mode is much more straightforward to process because you don't need to do this very fine alignment that you have to do in TOPS app. Yeah, so if you had access to TerraSAR X or Cosmos SkyMed, those satellites, those are all strip map.
ALOS-1, ERS-1, ERS-2,
all the
NVSAT.
legacy data is that, and yeah, the only other special case is ALOS-2, which comes in ScanSAR mode, which there is a separate workflow or ALOS-2 app that processes that.
Thank you. That's helpful. And actually, just one follow-up question. You mentioned Cosmos SkyMed. But like, how do you get access to Cosmos SkyMed data? Is it like easy to get if you're at a university, or
I have a friend in Italy. Collaborate with someone in an Italian institution.
Yeah, the Italian Space Agency does occasionally have announcements of opportunity that you can propose to get some data. There's also ALOS-2 data that's available for the geo super sites.
Yeah.
Over like Hawaii, Kilauea, and Iceland, and a few other super sites around the Earth.
The San Andreas Fault.
Yeah.
It's not easy. And the TerraSAR X is similarly, you have to often write a proposal to get access to that.
Okay. That's good to know. But like I might follow up if there are questions on that specifically. Yeah, thank you.
And I just saw on LinkedIn yesterday that Francisco Delgado got some ALOS-4 strip map data and was able to process it with strip map app. I think he might have had to do a small adjustment, but that's good news. I haven't seen any ALOS-4 data yet, but it's ALOS-4 also has a strip map mode. That's the new JAXA satellite.
Zoe has a hand up. we can't hear you, but I don't know if you have a microphone problem or if you're not speaking.
Zoe is muted.
She was unmuted and still no sound was coming.
Oh, she says technical difficulties.
Okay. Well, so maybe somebody else has a question.
Well, maybe Zach can go whilst we're waiting for Zoe.
Jump in just real quick. I was just curious about kind of trying to maximize the resolution of Sentinel-1 data. I was just curious about whether it's possible to do less multi-looking and less filtering to really try and maximize like the ability, and how fine could you go with Sentinel-1?
I believe that a colleague of mine that was looking at landslides, Al Handwerger, processed Sentinel-1 data with one azimuth look and two range looks to get roughly 10 to 15 meter pixel size. It takes a huge amount of disk space, and your phase unwrapping step might run out of memory unless you have a computer with like 128 gigabytes of RAM.
That's only if
So,
you do a full frame, I guess.
or you need to use the AOI feature to cut out a smaller area. If you,
Yeah, let us know how you get on.
In the later days, you can see a version of that. So you can always, with ICE2, form the full resolution interferograms, and then instead of multi-looking to make a big pixel, just do kind of a sliding window average, and that comes out with the same thing. Now the pixels are correlated with each other, and you've done multi-looking. You can get something that looks slightly sharper if you do adaptive multi-looking. So this was shown in the ISCE paper, where they have at every pixel, like not just a square multi-look window, but they try to only include pixels with similar amplitude statistics. And it still makes the output correlated, but putting it at full posting, so it's not the full resolution anymore, you kind of can preserve some sharper features. So you can play around with that and see how it looks. That's in Dolphin in day 5.
Should I try again now? Can you hear me?
You can.
Okay,
Yeah.
sorry about that. I was curious if you're trying to look at interferograms over a large region and you want to process multiple frames in the same track at the same time. How do you specify that in the in your setup? And sorry if I missed that.
We talked about it in office hours yesterday, which
Okay.
very few people were at. So what you do in the place where you define the reference and secondary SLCs, instead of naming just one file, you make it like a Python array of file names. So you put like a square brackets and then the file names in quotes separated by commas, and you name them in time order, which is the order that they show up in a directory listing anyway, and then it will stitch them together for you.
Awesome. Cool. Thanks so much.
But you better have a lot of space.
Or again, if your area is like halfway between two frames, then obviously define the area of interest and don't process the full thing.
Awesome. Thanks.
Colin has his hand up.
Yeah. I don't know if anyone else has run into this issue with the TopSap notebook, but I think with all the outputs, mine wound up being about like 80 or 90 megabytes, which like, pretty big for a Jupyter notebook. And for whatever reason, I think that might be like, I've been having an issue saving, just like exporting it as a PDF. I've gone through and have tried to like comment out as many of the cells that just like record the output of loops, but and then like rerun them to remove the loops output. But it's still pretty big. I'm not sure if this is like my figures in the notebook. But yeah, I've been having a issue saving it as a PDF. Was wondering if anyone else had encountered that.
It's usually the figures that take up most of the space in a PDF.
Yeah, I was just wondering if it was the looped outputs, because I've like looped output like long loops into a Jupyter notebook before, and that's like caused it to get really big and crash. But yeah, as
The
everyone else,
program
like,
that generates the PDF might be having trouble too.
yeah, yeah, I'll try saving it today. But yeah, was everyone else able to like save their TOPS app notebooks?
I just go down the bottom.
Sorry. I was able to save it, but I exported it as HTML file and then save it as a PDF.
Okay. Yeah, good idea.
I just go File, Print, which is right at the bottom of the menu. And I just had a look. I got 47 sheets, and it's quite happy.
Cool.
So it's right at the bottom of that file menu.
That was something. It was something that the ASF team were looking at, is like why it was sometimes crashing when people try to save it in certain formats. If people have been successful in saving it as HTML, that means that maybe it's been fixed.
Yeah. Cool. I'll give that a try. Thank you.
Yeah, thank you. So basically, and I guess a little bit as an introduction to today's class, I was thinking, when would you choose to process interferometric pairs or do time series? Like I'm imagining processes that are elastic and come back to the original state soon. For instance, on sort of a slow sleep, and then you try to watch that with InSAR, and then after a couple of months, the deformation comes back to the natural state. Will that kind of deformation, can you assess that with time series, or is it better to look at the individual interferometric pairs one by one, because the deformation is going to come back? I don't know if it's clear what I'm trying to.
No, I think so. Yeah, a time series is appropriate for that. You can often specify the functional form of your time series that you're how to say this. So the real place where these time series struggle is when you have a large sudden deformation within them. So gradual slow movement is something we can accommodate in a time series. Usually it's just when you have an earthquake or something, it becomes a bit trickier, and you still can try. It just sometimes doesn't cleanly estimate the earthquake deformation as well as you would hope. So yeah, if you have a slow slip event, I would try a time series approach, because it should work.
Okay, thanks.
Yeah, the big advantage of using a time series is that it can help you to separate atmospheric effects from the ground deformation effects. In fact, for relatively small earthquakes, I've sometimes used a time series analysis. In MinPy, you can solve for a step function, which is a sudden jump at the time of the earthquake. And by solving for the step function at the time of the earthquake, you can pull out the coseismic signal, even though there's atmospheric noise that would make it harder to see in a single interferogram.
Even Would you like to ask your question?
Yeah. Good evening. It's evening here in Italy. I wanted to connect a bit to Zach's, question, because actually I work with 5:1, so 1 in azimuth and 5 to range, and actually get pretty high resolution on my interferograms. But now I was trying on through the TopSap notebook. I was using the 3 to 7 to see if actually I had a bit of a difference. Actually, I don't find it that different, even though, yeah, you need a lot of memory, especially when I've been testing out the time series. You need loads of memory and RAM to actually run the full, like maybe in 5 to 3 years, even though if it's a short time series, it takes out a lot of memory in that case. So I'm probably going to do the same, but trying the 3 to 7, see if it gets better. And maybe I wanted to show, I did actually an interferogram of, because I work with very small earthquakes, so structures that have maybe length of 2 or 3 kilometers, and then we have like probably displacement of a few centimeters, maybe 3 to 6. So maybe I can share my screen if it's, I don't know if it's possible.
Yeah, it should be.
Sure.
I like small earthquakes, so that's cool.
Yeah, I think I should go on actual the TopSap notebook. Maybe I should just share that window there. Let's see if it's. Let me know if you can see my. So
yep.
This is the filter. This is the small earthquakes we deal with on Etna. So this is
Oh,
probably
yeah, that's nice.
so a few fringes, and that's what I was trying to do. One question is, I've had hard time on zooming in. So maybe it's something with, maybe we can modify around here. I'm not sure. I'm trying to get used to this with the Python commands up here. But I think if you zoom in, you can see it pretty good. And usually this is what we get on Etna. And this is the biggest fault, but then there's a few around here. This all the eastern flank actually has a lot of fault systems, and you have creep and cosmic events. So that's what we're trying to do. I'm going to try to do a time series so that I can see if there's a relationship between the two mechanisms, the creeping and the 6-slip events. So let's see if I can. So this is, and one last question is, do you think if a small earthquake like this, can we model it with the actual notebooks we were looking at yesterday during your lesson?
I would love to see you try.
That's what I
these
wanted
events are still elastic.
Okay. Yeah, because actually yesterday we were talking, it's not good if they're actually these are actually earthquakes. They're very, very like probably 500 meters deep. So very actual surface events. So I'm probably gonna try, and let's see if I get a good model.
Yeah, I'd be interested to see.
Yeah, that's beautiful. Very small, but very clear.
Yeah, small and very clear. Now I was trying after do the unwrapping, and then I'm gonna probably get my data and probably try to do some modeling.
Yeah, I don't know if you can crop the images in. You might have to edit the. I don't know what the complex plots function allows you to subset your data or not, but there might be a way of hacking the script to make it to allow you.
Yeah, because usually when I've been using ICE the last probably 3 or 4 months for my analysis, and what I've noticed is that sometimes it doesn't capture the bounding box I give it. So it looks like sometimes it just gets as a bounding box the dimension of the DM I put in, but then I can crop it through MinPy. So the problem is I have to create a big stack, enormous storage, because obviously then you're doing like probably 100, 200, 300 interferograms, big dimensions, but you don't need all that data. So then MintBy helps me to subset. But I think I'm losing a lot of time on processing the whole image when it's probably not necessary.
So there is this thing that ISF has initiated called burst to stack.
Yeah, and that's how I resolve the problem. That's what I use, the burst to stack, and that's probably one of the hacks. But in this case, since I wanted to go around with this notebook, I wanted to do actually how we saw yesterday in the examples. I wanted to, but it looks like the bounding box isn't respected as when I put it in. So I don't know. That's why today I was asking if there was a minimum dimension for the bounding box. It was related to this.
I don't know about the minimum dimension, but
no, but actually
usually
Eric
it's usually
gave me
the number of bursts that overlap with that bounding box is what.
Okay.
Yeah, it just takes a whole burst, even if you give a bounding box that's smaller than one burst.
Yeah. Okay. Perfect.
You need a
Thank you very
minimum
much.
of 2 bursts to process a TOPSAP interference.
Exactly. Yep. Yeah. Thank you very much.
There is a Mount Etna volcano super site from the Group on Earth Observations, Geohazards and Natural Laboratories super sites. So there is data from TerraSAR-X, Cosmos, SkyMed through that super site program.
Yeah.
For these very large, small earthquakes, I think you'd be better off trying to do look at these TerraSAR-X and Cosmos SkyMed than Sentinel-1.
Okay. Thank you very much.
More questions? We have 13 minutes left. Anyone have anything they want to show from the homeworks? Anyone want to show their interferograms or their models or anything?
And if you're going to process TerraSAR-X and Cosmos SkyMed, you have to use StripMap app, not TopSAP.
And we have that included as a supplemental.
It's in the supplement notebooks. This is a good question. So Leah asks, where do you incorporate masks for water? This is something that should have been included in TopSAP, but it's not. And that's kind of a flaw that we realized later, but nobody's gone back and added it. So some of the other apps, I think StripMap app and the ALOS 2 app have support for using water masks to you're processing data next to a ocean, and then it's better to mask out the water and not try to unwrap that. But TopSAP doesn't support that, so you have to apply a water mask after you finish your processing. That's just a flaw in the way that TopSAP was written.
Have you been able to get, there is a watermask.py script, but it's basically been broken for a long time as far as I can tell.
I haven't used that recently.
Scott looks like he's got thoughts about this, but maybe not.
I haven't tried to use
the
the
ALOS 2
ISCE.
app all the time. ALOS 2 app downloads the water mask
There are 2 types of water masks, right? There's one that gives you the land is ones and the water is zeros, and then there's water body masks, which are the opposite. And I think ALOS 2 app uses the water body mask, not the land mask.
Yes.
It's only a matter of like.
Yeah, there's a water body mask that came with the SRTM data, and that's what it uses. It's a 30-meter global water body database that was produced for the SRTM processing.
Anyway, there is a WBD.py and a watermask.py included in the ICE script, and I think WBD works, and I think the other one doesn't. I think it's hard coded to like the old SRTM repositories, and it doesn't find the files anymore.
Somebody should update that.
Yeah, and another simple way to create a water mask is just to use the correlation files that generated along with the interferogram. So the water are usually, because the surface changes so rapidly, there's no coherence along that. So if you have an average coherence and then you set a very small threshold, the first pixels you're going to detect is the water pixels. You sometimes also mask
But
out some
still
of the vegetation pixels, but that's usually not useful anyway.
I find a very small number of correlated pixels in the water always. It's just a statistical anomaly. You can also use the correlated components, the connected components file that Snafu produces as a mask for water, because the water, as you say, is always decorrelated and doesn't unwrap properly.
Thank you. Yeah, I had wondered if it was something I missed because I was looking at the Palos Verdes landslide in the example, and of course, there's a lot of water there.
Yeah, it's on the coast.
All right, 2 people have asked questions. Do you want to ask them out loud?
Yishuan, do you want to ask your question?
Oh, okay. Hello, and I want to ask if when I saw the result of the InSAR, and how if I could use the like polynomial fitting instead of like Gecko's data or Aero5 data to fit the arrow, is it possible? Or is it okay?
Well, this is going to be discussed in the session late at the end of this morning, or actually early afternoon here in California. That's the session 3.3. So yes, in some cases you can estimate something that removes a lot of the atmospheric effect by just using a polynomial or even a planar fit, linear planar fit, but it depends on the type of weather that you have and the type of signal you're trying to measure.
I have to say, I'm a bit of a polynomial fit skeptic ever since I had a student who worked on this, and it did very well, and it removed lots of what looked like atmosphere. Then we swapped out the DEM of the area for a different area, and it still removed most of the troposphere. So you have to be very careful that you can remove a lot of stuff just because correlations can be found. But I see Anne has probably got a more nuanced take on this.
Yeah, I can also add a couple comments. So depending on like you have 2 options. So the first you could remove like a linear ramp or a polynomial ramp in space, and that typically is pretty effective in removing some larger scale tropospheric noise structure. But you have to be careful because if you have a deformation that looks like a ramp, you might also remove that as well. So those kind of polynomial fitting, there's no guarantee you're removing noise or signal. They're just removing a pattern that happen to looks like that. And so in temporal baseline in time, if you're inverting for time series, you could also add a polynomial model in the time series inversion. And so again, you still have to be a little careful. So you need to kind of construct a model, perhaps of the deformation time series looks like a polynomial like signal. So you still, it's just sometimes it works, sometimes it doesn't, because it can remove both noise and the signal. So a lot of the time, these two can look very similar to each other.
Okay, I understand. Thank you so much. I'll be careful.
Five more minutes before the break. Get your questions.
Hello.
Hi.
I just want to ask that is there any quality parameters in InSAR that we can utilize to check if the atmospheric corrections are successful or not? I might not know. Yeah, but if you can comment on that.
I wouldn't consider it a binary, and In fact, the less you think of it as a binary, the happier you'll be. There is no success in removing atmosphere.
Oh, okay. So there is always a chance that we might remove it fully, or there is some residual as well. So
There.
It's
Go ahead, I forgot.
it's a noise. It has structure that helps you be able to filter it out. But with any filter, there is part of the thing you're trying to filter that will remain. And in some cases, like half of it can be left. In some cases, you can get 90%.
Yeah, we will talk a little more this afternoon when we talk about error correction. So a lot of those time series techniques was trying to design to mitigate some level of tropospheric noise. But you should remember that there's all going to be always a residual noise after your inversion, because it's a statistical measure. You're never going to know the particular day how that tropospheric noise is contaminating the data. We have some idea. So if you know your region and based on the climate model, you usually will have a rough estimate about the noise level. You can kind of derive that if you have a zenith delay from the GPS to know the variation and things like that. And also there are ways to kind of estimate the noise level in each individual interferogram, like using common sense stacking, get an idea about how big those noise is. Then you could do some error propagation analysis through the InSAR time series to get a estimate the residual. As a rule of thumb, if you're talking about those turbulence noise, which tends to be the hardest to predict from the weather model, which is usually a dominant case in a lot of the flat terrain, the noise level in your final deformation is going to be reduced compared to the single interferogram by square root of n, where n is a number of SAR acquisition. It's a rule of thumb, so give you a rough idea how big the residual noise is, and whether that's going to be important depending on how big your signal is. If you have a signal of 5 centimeter, 5 millimeter residual noise perhaps is not going to kill you, right? And if you're looking for 5 millimeter like transient signal, and then you have to be careful, because when you have the solution, it's going to be some feature, but there is uncertainty whether that's troposphere or the residual noise.
oh, all right. So it might be a serious problem in case of C-band, in especially when you are dealing in mountainous areas, because there is a lot of tropospheric effects and atmospheric issues due to turbulence.
Yes.
Yeah.
Yes,
Yeah.
and you should also realize that the tropospheric effects are the same for all wavelengths. And so just changing to L-band won't get rid of the troposphere. It's going to be the same. It only helps with the coherence.
All right. Thanks.
Yeah. And another way kind of to validate your measure is if you have some other data source, like a GPS data, you should always trying to do some validation and maybe use their misfit as an indicator of the residual noise level.
All right, great, thanks.
Well, it looks like we're at 10:49. So how about we take a 10-minute break, come back at 11, and Anne will be up to talk about time series.
I will talk, we have a joint session, me and Scott, in 10 minutes. Yeah.
Awesome. See you in 10.
Yeah.
Welcome back. If Anne and Scott are ready, we can give them the floor.
Yeah, so I will start with a shorter introduction, and then I will let Scott take over. And let me share my screen. Yeah, so this is a theory kind of a session, and I think Scott gonna maybe have a little bit of a more exercise at a later section. So let me get started. And so this session kind of gave you an introduction on how time series work. And my portion is rather short, and I would say it's a simple but my recommendation is that a lot of those more complex time series analysis techniques is based on the simple formulation, that is the SBAS formulation. So, and also I strongly recommend you, once you have a stack of unwrapped interferogram, because the SBAS formulation is relatively straightforward, it's actually useful for you to kind of implement it yourself. Using a short snippet of code, either through a synthetic data set or a real data set. So that kind of give you an idea how this error really have a role of impact. And then later when you move to more complex analysis, and then you can get a little bit better idea about how this trade-off between usually requires some parameter adjustment and how that going to influence your solution. So let's continue. As I recall, what InSAR measure is the phase difference between the two SAR position. And usually once you get the interferogram, the topographic phase is already removed. So what is really measuring is this phase difference delta phi that is can be related to the line of sight displacement at a ground pixel A between the two SAR position. And so here we have this straightforward relationship. The phase you measure from the interferogram and can be related to the line of sight deformation by 4 pi divided by lambda, where for C-band, lambda is 5.6 centimeters. And so what is time series analysis? So it's fairly straightforward. If you're interested in a very large deformation signal, and when we're talking about large in the InSAR content, I'm usually saying something like 5 centimeter or above, tens of centimeter. And these are usually the scale that is resulting from some volcanic activity or large earthquakes, depending on the depth of the deformation, can be different. So it's usually a large coseismic deformation or some excessive aquifer pumping in Central Valley can lead to this level of deformation. So in this kind of a case, you can typically just spot the deformation signature directly from a single interferogram. But for most of the cases, if you're interested in a small slow slip event or some of the more gentle, like groundwater pumping, and usually a lot of the case when you're talking about a centimeter signal, or in many cases like a millimeter level signals, and the chances you form an interferogram, and most of the fringes you're seeing is going to be due to various error source. And this is where a stack of interferograms. So when you have like one interferogram, you don't have a sufficient signal noise ratio. And an easy approach, like if I have 100 interferogram, and is there a way to consolidate the information that allows us, or thousands of interferogram, right? And so when I started, it was usually a stack of hundreds, and now we have thousands of interferogram. And so then is there a way to extract the deformation signal and better separate the noise? So it doesn't matter whether you're working with hundreds of interferogram or thousands of interferogram, the formulation concept is the same. So if you develop a code that can work in both cases, and the key difference is when you have a large subset, and then your accuracy, your ability to mitigate those noise gonna improve, right? And so the way it works as follows. And in a simple case, in a simulated case, so here red perhaps is a real signal of interest that I'm hoping to construct. And usually when you're say the time series, you're thinking of how the deformation is changing over time. That's D of T. And as we say, this line of sight deformation can be related to the phase history, phi of T. So this red signal is what we hope to construct. And in this particular synthetic case, I have a circular motion and on top with a transit motion. So this is kind of correlated to a scenario. Maybe you have a slow slip event that is on top of some kind of a long-term circular motion in the same directory, right? And then, so the InSAR data, you are typically requiring data at some regular intervals. Occasionally, you might have a spot that is missing. So each of these acquisitions is marked in red. And you can see that, and if what you're measuring here is the noise contaminated signal, that what we're showing here is a delta phi between T2 and T4. And hopefully, we hope to have many of those pairs. So you're forming interferogram using SAR acquisition of quite a T2 and T4, that's delta phi. And what we can written that is as our true deformation. And given this temporal resolution, we are not able to resolve exactly where that transient is because it's every 12 days, right? But what you can do is we can try to resolve the average velocity between T2 and T3. That's what we call the V2, and the average velocity between T3 and T4, that's what we call the V3. So this first two term is the approximated true deformation signal that we hope to reconstruct. And then there is additional noise term that leads to our deformation. And another thing I would like to mention here is that in this simplified form, the noise is added to each of the specific SAR dates. So you can imagine the true deformation, if there's no noise, you would get a measurement right here on the red curve and a red curve right here. And so this deviation from the true deformation signal is due to noise. And this noise is usually a characteristic of tropospheric turbulence noise. And you can see that if you have a particular day, that noise is added on that day. And any interferogram pair that formed using the T4 acquisition will have the same noise, right? And what is not showing here is in this summed noise term, there is also another type of noise, and that is called, for example, closure phase decorrelation noise. And these are pair dependent. So it's not the noise added to a specific date. It is when you are forming a particular pair, then there is a noise term that related. But nonetheless, for SBAS, it doesn't care. It is just a noise term. And the whole idea is it's going to be impossible for you to isolate this deformation signal using a single equation, right? But the idea is we can form many possible pairs. So for example, if we have a 7 SAR acquisition and we have M small baseline interferogram, what you can do is you can form 1 to 2, 2 to 3, 3 to 4, 1 to 4. So you have many of these different pairs. The maximum you could form is M times M minus 1 divided by 2, right? And so M 7 choose 2. And sorry, it's the number of acquisition, in this case, 7, Sam choose 2. So that's 7 times 6 divided by 2. And so M is going to be a number that is smaller than that based on your baseline threshold. And so each of the interferogram, you will be able to write an equation like what we're showing here. In this first equation, V1 is not included in the measurement because that is outside. You can just imagine there's a 0 times V1 there, right? And so you can write a similar equation, so M interferogram, M equation, and you can write it as a matrix form. So on the right-hand side, this delta phi is all of your InSAR phase measurement at a particular pixel location. And each line of B are the coefficient that is before the unknown. And if a particular unknown is not showing, that coefficient is just the 0. And all these unknowns, V1, V2, up to V6, is in this vector. So it's a standard linear system, a standard set of linear equations, and Python and MATLAB. Once you have the B formulated, and you can solve it just by a single operation, like in MATLAB, it's the backslash operator. And so the idea is pretty straightforward. And if you have a very large signal to noise ratio, this usually works, and you can get the velocity between each SAR acquisition, and then an integration of a velocity over time give you this deformation time series. So that's what we say, the deformation analysis. So earlier there comes in a place for a small baseline subset, how do you choose the threshold and why there is a difference between those solutions. So if you see this formulation, it's an inverse problem that in geophysics shows up a lot. And if you feed a different data, and then you're going to get a different solution if the data itself are impacted by noise in different way. So to better understand the quality of InSAR time series, we have to give a good idea of the noise, that's this term in our formulation. And in this simple sketch, you can see the noise is not too bad. But what I want to remind you is that the typically noise level for the tropospheric noise is centimeter level. The decorrelation noise can be much larger than that. And so if you're interested in millimeter level signal, you're dealing with a very, very low signal to noise ratio environment. So in a synthetic case, you could try these different noise amplitude and signal amplitude. And in this case, you know the truth. So then you are not going to be surprised about when you choose different noise compacted data, and you're going to see different solutions. So to better understand the noise level, so I kind of bring up a few common noise terms that usually, like depending on the site, will become a limitation for your analysis. So a few of them, like this orbital data, DEM noise, ionospheric noise, and some of them there are standard ways to mitigate that. So for example, orbital error, usually as long as your orbital precision is actually improved dramatically in the last 15 years, and also some of this ramp-like orbital error, you can remove a ramp, a linear ramp, and usually that's fairly effective. In a lot of the cases I have worked on. The DEM error, and as I mentioned, if you're using SRTM data in a relatively flat terrain, it's not going to be an issue. Usually when it is an issue, you can usually estimate that because it's a function of a perpendicular baseline, where your deformation should not be proportional to the perpendicular baseline of how far away the satellites are during this acquisition. The ionosphere, we're going to talk about that a little more in the later session, but in most of the cases, you're going to be limited by two major factors. The first one is tropospheric noise, and how strong that residual tropospheric noise is compared to your deformation signal of interest. That's because when you're looking at interferogram, most of those fringes are actually from tropospheric noise, and spatially they share a lot of the common characteristic of your deformation signal, and so that's come up a lot. And a second term is the decorrelation and the phase unwrapping error. So these two kind of are connected, because when you don't have any decorrelation, your phase is coherent. Phase unwrapping is typically straightforward. You're not going to have error. This algorithm works very well when your phase is smooth in time, so the algorithm can count those fringes just like your eyes can do that. And I try to compete with a SNAFU algorithm. I find my eyes actually a little perform worse than SNAFU. So when you have decorrelation, when your eyes cannot see these coherent fringes, you're going to start to have this large unwrapping error. And phase unwrapping error, every time you have a phase unwrapping error, is a minimum of 2 pi. So, and sometimes it can be many cycles of 2 pi. So this is a fairly large error. So when this comes up, it must be mitigated in some way. So that's also an issue. And so give you an idea how this error looks like, I'm showing you an example of the Sentinel-1 interferogram over the Houston area. So you can see in this Houston downtown area where you have a limited vegetation, here, the fringes is actually due to deformation from groundwater pumping. So it's a fairly large signal that is visible even in a single interferogram. But besides that, you can also see kind of like gradient-like fringes right here. It's also spatially coherent. So these are due to tropospheric noise. Why we spent some time on this, did some validation, and I attribute that. So I will just tell you the answer right away. So you can see that both the deformation signal and this tropospheric noise is kind of coherent in space. So your SNAP phase unwrapping usually has not a lot of issue in this kind of area where you have a coherent patch of data. So once you're moving to kind of vegetated area, and you can see most of the phase when you zoom in is completely random. And this is what we call the severe decorrelation. And in Houston area, there are some like minor decorrelation. So these looks like random noise added in space. So usually the minor decorrelation is not an issue. You could apply some spatial filtering to get rid of this spatially incoherent signal. But the issue for the severe decorrelation is once this kind of decorrelation noise is beyond the phase of 2 pi, it was added to the wrapped phase. It just completely decorrelate your signal and you don't have any useful information. here. So that's kind of how this two noise is introduced, and also what they looks like in your data measurement. So how are we gonna deal with that? So my personal preference is trying to kind of isolate this two component whenever I can. So for example, in the Houston area, you're gonna only have mostly tropospheric noise that looks kind of like the deformation noise, right? And so you don't have to worry about decorrelation. And if you don't have to worry about it, don't worry about it, because because sometimes most of mitigation strategies require you to track how it performs. So if decorrelation is not an issue, I don't think in this kind of area, either you use SPAS or PS, you're going to get a similar type of result, because there's no decorrelation in this region. And so in outside the region, the whole idea, one of the straightforward idea, and Scott can talk a little bit more on the other idea, is that you could use some kind of measure to get some of this high quality pocket of data. And those are what we call the persistent scatters. And so the reason they call it the persistent scatter is these are like maybe a rural town, a road, that although everything else is vegetated, there is a small number of pixels that you can see is a pocket of a coherence. So there are many ways to detect these pixels and then perform time series analysis only in this pixel, and don't trust these other regions where the phase is unreliable. And so decorrelation characteristic, the good news is with ISAR L-band, you're gonna see much better quality in terms of more of the data gonna looks like this downtown area rather than this completely decorrelated area. So it's wavelength dependent. And so here we are showing you interferogram over Hawaii's Big Island, the south flank of Kilauea for X-band, C-band, and L-band data. And usually X-band, you won't have any coherent in this rainforest area. You have been there. And so on the south flank, it is sparsely vegetated. So what you can see is all those different wavelengths, they have a good coherence over sparsely vegetated rocky area. And so decorrelation in this case is not an issue in any of them, right? And so then in this forested area, then the L-band would have a substantial advantage. And it's likely with a 12-day L-band data, then it become a lesser issue, and maybe a standard SPAS that works for rocky area will work for some of the moderately decorrelated area. And so how to mitigate that? So for decorrelation, what you could do is, here is originally moderately decorrelated interferogram, and you could apply a spatially filter to enhance the correlation. This usually will speed up your phase unwrapping and reduce the phase unwrapping error. So where we're showing here is what we call a ghosting filter compared to a standard box filter. It's a little bit better at preserve those densely variant fringe patterns. And so all you can also just do multi-looking, and by choosing maybe 120 pixel spacing and a multi-look interferogram from single look images, and that will reduce your image size, and also you will see an improvement in coherence and a reduce of a decorrelation noise. And so once you have all a reasonably good number of interferogram, you can always go back to this time series analysis. How do you separate the true signal from deformation? The key is we're going to talk about some mitigation strategy you can apply on the interferogram phase to remove some of the estimated component. And then there are some kind of residual turbulence noise. And what I have found is most effective is when you change from have 10 interferogram to 1,000 interferogram, and you have this redundant measure, so that a very densely measure, you could apply a temporal filter and to remove some of those random jumps in your time series. They're usually tropospheric noise. So the key difference between deformation and tropospheric noise is tropospheric turbulence noise tend to be random in time, while the deformation tends to have some kind of a characteristic like a circular motion, a transient motion. So you could incorporate a deformation model that align with the signal you're looking for. So hopefully that will help you to better isolate these two components. And at the end, before I leave it to Scott about how are we gonna choose mitigation strategy. So for the standard small based on subset method in the above formulation, the way to choose to mitigate the decorrelation so that you use a high coherent deformation focused on the separation of tropospheric noise and signal is using small baseline interferogram because of it's more likely to decorrelate over a longer temporal baseline. So this works very well if you have your site suffer from minimum or moderate decorrelation. And the only caveat is you don't want to limit it to only 12-day interferogram because of the closure phase in that case can blow up. So ideally, you can start something like 180 days to see how it works. And usually if your data is consistent, you should be able to change the temporal baseline within a reasonably range before you see severe decorrelation, and they should give you more or less consistent inversion result. So in densely vegetated region, SBAS solution may be unreliable, and when you're using a coherence mask, you might mask out all the pixels, or sometimes you find the coherence mask is a data-driven approach, is biased depending on a lot of other factors, may not be a good measure to distinguish a good stable pixel versus a non-good pixel. So these good ones, sometimes we call it a DS, distributed scatter or persistent scatter, and we'll let Scott to talk more about some more advanced algorithm that is built upon the SBAS. Scott, you're muted.
Sorry, am I sharing a window or I want to share a screen? Share. Okay. Do you see my terminal or do you see my Zoom?
Terminal.
Terminal.
All right. Switch it over. Okay. So I'll pick up where Anne left off. It actually
You're in presenter view, or you're showing us your presenter view.
Well, that's not very useful. Still not useful?
Still not.
Codswallow.
Good use of antiquated swear.
You know what? I'm just going to share that window. Sorry about this.
Oh, no problem. There is a way to, like, is it kiosk mode? I forget what it is, that you can actually present in a window on your machine.
Does that look better?
That looks great.
Okay, thank you. So this is Harish Fatahi's slides for the most part. I've added some new things, but he has given this talk on time series analysis for a few years in a row. And we'll jump to the new stuff pretty quickly, but just to reiterate that the inputs to time series analysis starts with the co-registered stack of SLCs, which you've all made now with ISCE 2. Then you put it into some box, which there are many variants, and then you come out ideally with n displacement epochs. You can also come out with something like an average velocity, some seasonal fits. But for this talk, we're going to talk about how the goal is to get the same number of input dates as output dates. And as a reminder, at each pixel, you'll have a line of sight displacement, and it'll be relative in two ways. So it's relative in space to that yellow reference point, and it's also relative in time to some reference date that you are assuming is 0. And this happens because your measurement are differences. So inherently, when you measure differences, you will have to have something that's 0. Changing the reference date is a simple shift up or down of this time series. So Anne talked a lot about the noises and pointed out correctly that the dominant noise source is often troposphere or decorrelation noise. And for many years and many satellites, the decorrelation noise was the hardest part. And so most time was spent overcoming that. And so people came up with very widely different techniques for working around that. And some of it sounds very different. In my view, a lot of times it's a general process of make interferograms that look good and then pick out the pixels that are good from there. So diving into how people have actually done that, it started with what was called permanent scatterers in Ferretti's first paper. Later, since that was trademarked, we called it persistent scatterers. The theoretical perfect persistent scatterer is one that has a very strong scatterer that dominates all of the other clutter within that resolution element. So I believe you guys looked at this in the SAR theory as well. But the idea is if there's one part of it that has very strong amplitude, then each of these little things in the cell, they all contribute some rate of return, but they'll be overwhelmed by this. And a way to see this is to look at the phasor diagram. So another way is each of these is a complex number that returns, and you simply add them all up. And the way you do that is you add a bunch of vectors tip to tail. And so this strong one is the signal that you hope to measure, and I've set it to have 0 phase. The rest of them have a random real and imaginary part, and when you add them all together, they add up to this red little tail. And because the dominant part is so strong in amplitude, it doesn't affect the phase, which is the angle of your measured to 0. So if you really want this 0 phase measurement and you end up with something that's 3 degrees, that's still quite good, even though you haven't done any multi-looking. So this is all assuming that you're working at SLC full resolution. And that's one reason why people like the persistent scatterer technique, especially in urban areas where the persistent scatterers are dense. But often you don't have many situations where there's a super strong return in one cell. You have something that looks like this, which we call distributed scatterers. So in every SAR element, there are some things that give signal, but they all have pretty low amplitude. And so when you add them up, if you want to get the signal, it's not very large compared to the noise. And so when adding up all of these phasors ends up with a complex number where the angle or the phase that you measure is very far off from the true phase. So here, a single look DS might have humongous error, and essentially, if you look at the full resolution interferograms, it'll look like mostly noise from pixel to pixel. But the idea with most DS, basically all of DS techniques, is that there is some signal here, and if you simply add up a lot of the DS in a surrounding area, then you can come up with something that has much lower noise. So if we pretend that we averaged a bunch of SLC pixels that all have the same signal, different noises, then the signals add up in the same direction, and now we have an error that's much lower and is closer to the PS error. So we're basically trading coarser resolution for lower noise. So as I said, I think a lot of times it can feel arbitrarily different when people talk about, do you use PS here? Do I use DS InSAR here? It can be a gradient from good, really strong pixel to weak distributed scatter pixel where you definitely need to multi-look. But historically, people treated them very differently. And so for that reason, we'll look at how the PS were described first and then what people came up with for DS. The first PS technique that got very popular because it worked quite well was Ferretti's amplitude-based selection. So in 2001, he outlined a lot of the theory around persistent scatterers, and his selection technique was very simple, and for that reason, it was useful and popular. He took that phasor diagram and he said, well, if we know that a PS has a very strong return, we don't need to look at anything else besides the amplitude. And so what we can look at is, for a pixel over time, how strong is the amplitude? That is, what's the mean amplitude? And how much does it vary? So what's the standard deviation of the amplitudes? And you would do this at every pixel in the SLC. And pixels that have a low standard deviation relative to their mean, we say they have a low amplitude dispersion index. And that's good. It doesn't get dispersed. And additionally, he outlined a pretty good approximation where at very high amplitudes or low dispersions, you can make a good approximation of the phase standard deviation, which is really what you want when you want to see how good your INSAR is, because the phase is what you care about. So by computing this quantity, you also have a near one-to-one estimate of how much standard deviation you expect in your interferograms. So this works great over urban areas. People started to apply this to other areas that were more vegetated or just sparser buildings, and they found it didn't have very high density. So people started to use the phase to select more pixels that were pretty good, but harder to pick out from just amplitude. And this is a lot of text here, so I'm mostly going to skim over these various phase-based selections. The first one was Andy Hooper, where he had the idea that the correlated noise, or the noise sources, can be divided into correlated terms, like the orbital or the tropospheric noise, and the decorrelation part of it is not correlated in space. So if you can remove it with a bunch of filters, then you can get a good estimate of which pixels actually have low phase noise by ignoring the turbulence and the orbital ramps and the other ones that you can remove. And with that also works very well. Stamps has a number of other improvements, and it was just well implemented. It was open source, so it got very popular, and it still works well today. People use it. But people could do better and continue to build upon just more successful and fancier persistent scatter selection techniques. One of them that Piyush Agram came up with, so one of Howard Zebker's students, was a way to estimate the PDF by using the signal to clutter ratio. Again, I'll not spend too much time here, but he essentially has another cheap to estimate way to find which pixels have low phase standard deviation. And with that, you could pick out more. Moving forward a bunch in time, one of Anne's students in our lab, he came up with a pretty different way that works quite well, actually, and it uses, rather than a PDF model of the noise, it does a very simple cosine similarity metric. So it looks at nearby pixels, and at every one you want to see how similar the phase is, because that can ignore large variations in troposphere, and essentially pixels that agree with each other in space will have a high cosine similarity, and ones that are in a super noisy area that you don't want to pick and you don't want to try to unwrap, they have a low cosine similarity. And this works well because it's simple, and it also is pretty resilient to a blurring effect that can happen when you do a lot of spatially correlated filters. So the outputs of a PS time series analysis can look something like this, where this is actually Sarah Mirzai, who's on the call, her Miami analysis. So for this one, she started with the amplitude dispersion of Ferretti, because that's the simplest to look over and see what the results and the intermediate quality metrics are. So using 160 SLCs for 7 years, you can compute, again, the standard deviation of the amplitude divided by the mean. So where things are bright in here, that's actually bad. That means it's a high standard deviation relative to the mean. So we see the water here has higher amplitude dispersion, and the urban areas here with really tall skyscrapers have low amplitude dispersion. And so you can do a simple threshold and pick out pixels that have a low amplitude dispersion and call them your PS pixels. Then you take the interferograms, which were traditionally just single reference, because in theory, a persistent scatter is persistent and constant over time. And so you only need to form one set of interferograms and not a redundant network or anything. And so with her analysis, she found some clear subsidence in Miami Beach. And you can see here how it's relatively dense around all the urban areas, but in the golf courses and other vegetated, the amplitude dispersion will pick nearly nothing. So if your study area looks not necessarily like a golf course, I wouldn't recommend studying a golf course. But if it looks vegetated, then you'll probably need something with the distributed scatterers. And the first way that somebody came up with to use the rest of the pixels that aren't simply very bright pixels was the SBAS technique, so the small baseline subset. The core idea of that, as Anne said, is very simple. You make some set of interferograms, and the idea is that interferograms with short temporal baselines and short perpendicular baselines are going to have higher coherence. And people will form networks like this. If you've seen figures and been confused by this, don't feel bad. It's a little confusing, but the idea is to show an overview of what data is available to form for interferograms. So you can make a plot of each green dot is a SAR acquisition, and over time they'll be in different positions on the orbit. And so this is probably one that's not Sentinel-1 because for one, the time period doesn't make sense. But for older satellites, the perpendicular baseline varied a lot. And so you wouldn't want to form an interferogram that has a 2,000 meter perpendicular baseline. And so you can make some kind of network where everything's short perpendicular in space and short temporal baseline in time. I'll also just note that these diagrams, you can make them still with Sentinel-1 and with ISCE, but they're less useful because everything is going to be super squished here. And these make the most sense when the axes are scaled roughly so that a unit in perpendicular space leads to about as much decorrelation as a unit in time, but that can be hard to do. So Anne described what you do with this network. You form the interferograms, you unwrap them, and then you create your system. And the system has observations that are your unwrapped phase. Usually, or for the original SBAS paper, they treated each pixel independently. Some people have formed joint networks, but the common thing is to just make each pixel independent and solve it one at a time. The design matrix is, in the simplest form, each row is either -1 or 1. So that's where you're solving directly for the phase time series. You can also form the velocity version where you're solving for the velocity between each date and then integrate after. And you can do whatever inversion you want after. People have come up with a lot of fancy weighted inversions minimizing the L2 norm with least squares, or if you don't have enough interferograms, that's SVD. You can minimize the L1 norm. There's many ways to invert this, and you end up with a time series of unwrapped phase at this given pixel. In MinPy, you can also see the inversion quality, which is called temporal coherence. Temporal coherence is definitely an overloaded term in InSAR. Most processes have some kind of temporal coherence, which is basically after you do an inversion, how much do your results agree with the input differences that came in. So you kind of reform the differences with your results and then scale it from 0 to 1 of perfect agreement or complete garbage. So those are the well-known ones that have been around for over 20 years. About 10 years after SBAS, people came up with the idea of phase linking. So this is another one that can sound very complicated, but the core idea is pretty simple. When you start with your stack of n SLCs, rather than forming some network of smaller ones, you form all possible interferograms. And then you do an optimization on the wrapped phase before you do any kind of unwrapping to end up with a wrapped time series. So you'll end up with n-1 phase differences before doing any unwrapping. And these are supposed to be cleaner phase filtered. There's a lot of ways you can look at it. They can be the best estimate if you form a probability model and then you do some kind of maximum likelihood optimizing. Another way to think of it is that you're basically making a distributed scatter, which after you've multi-looked, it no longer has the same properties as a PS. You make it look like a PS again by getting one single time series. So what this looks like in a little more detail is that another thing people have called, besides phase linking, is covariance methods or coherence matrix methods. And the reason is that at every pixel, you're going to make a coherence matrix first by centering around there, multi-looking, and forming every interferogram. So for n SAR images, here we have n 0, 1, 2, 3, 4, 5. So 6 SAR images. You make an n by n coherence matrix, so it's 6 by 6. The top and the bottom are the same. They're conjugates of each other. So really, the top is all possible interferograms. So the diagonal is 1, and say row 1, column 2 is the interferogram from reference date 1 to secondary 2 conjugate. Then once you take this matrix, you do some kind of optimization, and there are a lot of kinds people come up with, and you want to get one vector of 6 phases. And so you have 5 phase differences. So we can visualize what this turns out with in the final full image space by a synthetic example. So for this one, I've simulated about a year of data where we have a way to simulate turbulence noise pretty easily. That's in the library. And I've also simulated an exponential decay of correlation. So the SLCs that we have, we have the model that over time, the coherence dies out in an exponential fashion where the time constant is about 60 days. So after 60 days, it should be about 0.3 coherence, and beyond that, it drops very low. And I'm comparing doing a small amount of multi-looking to try to preserve resolution, keep it high resolution. I'm doing more multi-looking of boxcar window with 12 by 12 looks. I'm taking a Goldstein filter on top of that to see if I can make this phase even cleaner. And then I'm doing this phase linking technique where I've taken the same size window as this multi-looked, but it's actually, the output is the same posting as the input because I'm simply sliding the window over time or over each pixel and keeping it the same output size. So after 1 month, there's not much decorrelation and you see very little difference. So this is why SBAX works. If you only work with interferograms that are this clean, you can get a pretty good result. After 4 months, the lower multi-look starts to look pretty bad. And this is why people say you really should multi-look if you have any kind of strong decorrelation. You can still preserve the correct phase by doing more multi-looking, and the Goldstein makes it even smoother. After the full year, the low multi-look and the high multi-look basically turn into pure noise. And this is demonstrating also the Goldstein filter isn't magic, that if you feed in something that's very high decorrelation, it will keep the same high decorrelation and not do anything. But the phase linking is able to estimate that phase, and that is possible because it gets the benefit of looking at all possible interferograms, including the long and short ones, and optimizes together before we unwrap. So in the slides that we'll be uploading, there's the links to the different optimizations that people have. The simplest one that I have in the demonstration notebook is to take the dominant eigenvector. This is, if you've heard of the concept of PCA, principal component analysis, this is basically the same thing. The other two seem a lot more complicated, and if you're interested, I'd encourage reading both papers, which are pretty well written, but they start with a SAR noise model, and they walk through to get the optimal, the quote, optimal estimator under their probability model. So they call it's a maximum likelihood estimator. So the benefits of phase linking is that, as we saw, for some kinds of decorrelation in some scenarios, the wrapped phase can show much lower noise after you perform phase linking. And this, one reason I like it is that it can be less parameter tuning and network adjustments after the fact. A lot of times, if you pick pretty good parameters, you can get good results for a very wide variety of sites. And Anne mentioned the closure phase problem, and we'll have a slide on that in a little bit, but it will reduce the impact of that by performing this optimization in the wrapped phase domain. And if your implementation is good, the computational impact is not that strong. It's not super slower than SBAS. You're definitely doing more work, but as we'll see in the Dolphin library, it runs pretty fast, so it's pretty good. But I wanted to put the workflows in this manner to show that there's really not a humongous difference of the two DS techniques of SBAS and phase linking. The key is here, you start with the same input co-registered stack. For phase linking, you then do this covariance-based optimization. And so you have a time series of wrap phase. You can then reform a network if you want, and that aids in the unwrapping because it can still be easier to unwrap shorter interferograms even after you've done this optimization. And so the difference here is now you both unwrap, now you have a network of unwrapped interferograms, and then you have to invert that to get your unwrapped time series of displacement plus noise. And so afterwards, you both have to post-process. So this doesn't like get rid of atmospheric noise or anything. This is just to get a cleaner phase and deal with the decorrelation noise. Two final notes is Dolphin also implements the sequential estimator. So if you have something like 300 SLCs, it's not worth it, and it's super slow to do the covariance for the full 300 by 300. You can get nearly as good or better results by breaking it into batches, which they call mini stacks. And they do an extra step of called these compressed SLCs, which we won't get into now. But basically, you can think of it as they batch the covariance matrix, and you get nearly as good results, and it's much faster. And the other thing I wanted to touch on, because I think it was on the syllabus, is that if you've heard of PS-DS hybrid techniques, really that is just literally running both versions of this. And so Dolphin has this where the first step is to do an amplitude analysis, and then you pick out a very sparse subset of PS pixels, and those phases you're going to set them aside. And then you do your phase linking, and you get a time series of wrapped phase. And then before you unwrap, you simply override the locations of the PS pixels. And that's all the hybrid approaches are, is you do phase linking, and then you insert back and overwrite the PS pixels because you think those are good and they don't even need to be multi-looked to have lower noise. So we're running to the end of time. So we have some examples. These are Haresh's examples showing how much denser the results are when you have the PS and the DS. And you can pick out creep events in California, as well as seasonal, all the time series good stuff that you'll see in MintPy. The covariance analysis can actually be pretty interesting to see strong changes. So this is what a covariance matrix looks like after an earthquake event, that any kind of difference where the surface is completely changed, you'll get this like block diagonal covariance look, where over here are interferograms in the before to after, and so they don't work, but before to before has high coherence and after to after has high coherence. So this is do with that what you will for finding damage proxy, cool machine learning techniques. Other examples of recent Opera PS-DS analyses. My colleague Brett Bazanga did a nice analysis over Houston for the infrastructure there. Al Hanberger he wrote a good paper on Palos Verdes. So this is the results from Dolphin for the landslide results, and it captures it quite nicely and keeps a pretty good resolution by having that moving window phase linking technique. And as far as the parameter tuning, this is just showing that with the defaults that we're running over most of America, we were able to get a pretty good match to the very hand-tuned ARIA research from Marin's paper, as well as the older Xiaohua's very good map of all of the California and the creeping events and the basically the entire San Andreas fault system. So I think we're coming to the end, but luckily Anne did touch on a lot of these errors. The one I wanted to make sure I got to, because it's relatively new and the least understood, is the closure phase that people have referred to a few times. Basically, closure phase is if you take interferogram 1 to 2 plus interferogram 2 to 3 minus interferogram 1 to 3, so or plus 3 to 1. You would hope that was 0. It will never be 0 when you multi-look because of the weird nature of complex multi-looking. But a lot of analyses were assuming that if it's not 0 when you do your inversion, at least it's hopefully averaging to 0. But people started to see in the beginning of 2020 that that's not true, and there's some cases where it's systematically biasing the displacement results. And some people don't like the word bias because it is a real signal that here she showed that this is Yuji Zhang's paper. The displacement has a bias that goes up over time when you only use short interferograms, but it actually is a signal because these small pulses in gray are the rain events. And so it is possible to estimate soil moisture if that's what you're doing. It's very hard in active area research, but this is kind of the diagram that shows don't use just nearest neighbor interferograms, and otherwise you may get very strongly biased results. So this is 4 centimeters off in 4 years. So I think we're out of time. So we have all of the open source tools. We have the demo notebook that I probably won't get to right now, since I think we're supposed to take a break, and I don't want to not take the break.
Scott, I just answered a question on chat or on Q&A that asked if Dolphin can work with ALOS 2 data. I think conceptually yes, but technically currently no, right?
Dolphin can work with any GDAL readable co-registered stack.
Oh, okay.
So if your file format is normal enough to be readable by GDAL, then Dolphin can work with it.
Okay, so there might be a little bit of data smithing that needs to be done to get the data format right, but if that's right, they can work with it.
Yep, yeah. I mean, if you're doing ISCE and it has the VRTs, then you just point to the VRTs.
If you're prepared to be a guinea pig and try it out.
I mean, the first time I tried Gamma, that somebody sent me a zip file, it worked.
Cool. Yeah, I think we should take a break. Come back at noon, which is 8 minutes time. And we'll move on to interferogram stacks, which are the inputs to these time series codes. We're back from break, you know.
Do we have time to go to Alireza real quick, or do we need to hop on the next topic?
Well, what is Alireza trying to ask here?
Sorry, I have a quick question from Scott. Scott, so you mean we have to prepare our stack of let's say a stack of SLCs through ICE and then pass it to Dolphin? This is my first question. And during your talk, you said that if you have 300 SLCs, it's not computationally efficient to do it through Dolphin or something like that, or phase linking. Can you please repeat it again? Sorry about the interruption. You are muted. Sorry.
First part, it doesn't have to be ICE. It's just Dolphin doesn't have its own like low-level stack processor like ICE2 and ICE3 and Gamma and all the others. So there are ones that can make a co-registered stack. So that's the part you have to prepare in advance. It can be ICE2 or ICE3 or Gamma. It just the data has to be something that GDAL can understand if you do GDAL info on it. The full stack is more that, like, a lot of the times phase linking is called like the full covariance method. So if you have 300 images, a full covariance would be 300 by 300. But my point was you don't need to do that, and Dolphin doesn't do that. It'll do by default like batches of 15 to 20. And so it's not very slow to work through 300 images.
Thanks. Right, let's move on. Eric is up next to talk about standard products and interferogram stacks.
Hi, yes. So going to be talking about some pre-processed interferograms. These are the products that there are several different types of pre-processed interferograms that are around, but the ones that are I'm going to talk about today mostly is the so-called ARIA Sentinel-1 geocoded unwrapped interferograms. So these are a product that's been processed from the Sentinel-1 data at with ICE2 TopSap, and they did some preparation to make the frames in a standard location by working with the burst database instead of dealing with the slices moving around that we talked about earlier in the question session. And these geocoded unwrapped GUNWs are a data format that's highly similar to the geocoded unwrapped interferograms that are going to be a standard product from NISAR. So we think it's a good thing to get used to you working with these geocoded unwrapped interferograms, because that's going to get you a good start on being ready for NISAR. And in fact, we had in an early stage of doing this ARIA processing, we actually got funding that was called Getting Ready for NISAR, GRFN or Griffin. So it's definitely a way to get ready for NISAR, and it's a very useful product in itself. And they've processed these geocoded unwrapped interferograms for several different places around the world. They're not available globally, but they are available for the West Coast US, the East Coast US, places in the Middle East, Tibet, some places in like Hawaii, and some other places around the world, but they're not global. So let me share my screen. This is the so if we go to the ICE Plus directory here, there's a directory called it's under 3.2 interferograms. I guess before I get started on the ARIA GUNWs, there's also other products. There's the ASF has an on-demand processing system. It uses called the Hype 3 Gamma processing. That uses the Gamma software commercial package to process interferograms, and it produces a product that's not exactly the same as these geocoded unwrapped interferograms. They're not in the same format, and they require a little bit different pre-processing, but they're somewhat similar. And that's a way to, if you want to process similar data sets for your own area. So there's two different notebooks here. One is called ARIA Extract tutorial. That's this one. The ARIA Extract program is a way to just extract some views of the data. So this is a sort of a way to download some data and get a first look at it. And I'm just going to run this and then go through the cells while it's running. So the key thing is that these interferograms are geocoded. They're already on a geographic grid. That geographic grid has a spacing of 90 meters. So these are multi-looked. I forget, I think it's 19 range looks and 7 azimuth looks. And then it's geocoded at 90 meters. Or since it's covering huge areas, it made sense to make a relatively large amount of multi-looking. These are for looking at large areas, not for looking at very small areas. So if you're looking at a landslide that's only 200 meters across. That's going to be hard to see with these 90-meter pixel interferograms. The ISAR interferograms are going to have a spacing of 80 meters. So these are actually quite similar to that. So this particular data set, sorry. Looks like a junk phone call. So the data it's a HTF5 format. So this is a hierarchical data format that's it's a way of keeping lots of data together in one file. The Sentinel-1 data sets come with a zip file. That's one way of sort of keeping a bunch of files together. HTF5 has a different, it's actually physically a one file. You can't unpack it. It's a file that has a whole number of different layers and also metadata. So it's a type of file that is used more and more these days because it's an efficient way to keep multiple data sets together and provide the metadata about what's the position and what's the spacing, and also about what these different data layers are. So it actually, so like one of the pieces of metadata that's in there is the bounding box of the product. Another then there's there's layers that are telling you about the oops. You double click it unformats it. The about the geometry. So this is the azimuth angle, in a horizontal direction of the line of sight. The incidence angle, that's the angle from the vertical, the look angle, and the perpendicular baseline of the pair. So these products are just one pair of an interferogram, and that has a certain baseline, which is encoded into the file. And then there's the data layers, and the data layers are basically you kind of all those standard ISCE2 outputs, the filth.topophase.unw.geo, that's the unwrapped phase, geocoded, that gets sort of rewritten and made into a layer in this GeoNW file. So that's then becomes two different layers. There's an amplitude layer, unwrapped phase layer. There's another layer that's the coherence estimate, and then also the connected components that we discussed yesterday. That's another layer. And so these are all in one big file, but they're stored as layers in that file. So this ARIA extract program is a way to look at those layers and see what the layers have. So like we did for the TOPS notebook, there's a pre-staged data set.
Eric, there is panic in the Q&A that you're using a kernel that people don't have.
Oh, yeah, sorry. You can use the I developed this with the ARIA tools kernel, but they've now updated the EarthScope InSAR kernel to include all this ARIA data set. So just to prove to you that it works with the ARIA, with the regular EarthScope kernel, I'm going to restart it and run all the cells again. Yeah, sorry. When they first started developing these notebooks, the ARIA tools were not included, but now they're included in the EarthScope InSAR environment, so and kernel, so you can just use that. Sorry, I should have done that.
Thank you. Thanks for the explanation.
Okay, so
And I
there
can
is
use this
a-
opportunity to tell you that tomorrow you'll build a kernel. We'll be using a different kernel tomorrow, and I'm going to show you how you can create one using a notebook. So we'll go through that exercise tomorrow.
Okay, yes. So there is so GDAL, that great graphics data access library does have an HDF5 driver, so you can actually, but you have to make sure you have a recent version of GDAL. I think this error was sort of an older thing because when people didn't all have the latest version of a version greater than 3 of GDAL, I think you can't even find an older version now. But so ARIA Tools is now included in this Earthscope InSCAR kernel that we have on these computers. So like we did before, there is a stage data set that I'm using here. We import a bunch of stuff. We set up the work directory. I'm going to do this directly in the where the notebook is originally located. It downloads this aria extract.zip from the S3 data set, S3 simple storage system from ASF. That includes these two products. So you can also search for these products directly on the ASF search. Maybe I should take a quick diversion to look at the ASF search again, just to show you that it's there. Search.
Very meta that you search for search.
Okay, where is this? I don't remember what that is. Let's just delete that. Clear search. So let's just do Los Angeles. So under data set, there's down here, you can find ARIA S1 GUNW. So I can search for that. Find that there's actually around 300 of these, 250 for the Los Angeles area. One of the things that's there's actually different versions of the ARIA Tools products. The most recent version that has the standard frames is this version 3.0.1. Some of the older files are also available in some places when you do this search, and those have the frames shifting around. That's before the ARIA project figured out how to redo the bursts and make the standard frames. But we can see here that it's a standard it's an interferogram. It's for these two dates. The start date is this is from March 10th, 2025 to February 26th. So this is earlier this year. They're both Sentinel-1A scenes. There's a 12-day interval. So it's one interferogram that's 12 days. And they're about 50 megabytes apiece. By doing that multi-looking and doing some extra tricks to make the files small, they're about 50 megabytes. So this allows you to work with a large amount of interferograms without having to download terabytes of data and process them. And this is basically, it's because it's all it's multi-look to 90 meters. It's really intended for SBAS time series analysis, not for, you can't do any of the PS dolphin or any of those other types of analysis. So in this stage data set, there's two scenes. They're from the file name here. It tells you what it is. It's Sentinel-1, GUNW, A for ascending, R for right looking. It's track 124. It's TOPS mode. The first date is 2018, May 2nd. The second date here is 2018, April 8th. The ARIA GUNW files are always processed with the later date as the reference and the earlier date as the secondary scene. That's the convention that they decided to use for this processing. The second part of this part of the file name is the time. In UTC time, it's 04 hours, 30 minutes, 52 seconds. And this second one is another frame that's for 26 seconds earlier. And then it also actually gives you an approximate location for this scene. This last, the PP means it used the precise orbits, and this last number is just a run number. So that doesn't actually mean anything that you can use. But if the data gets reprocessed, it has a different number there. And the last part here is V301. NetCDF, it has a .nc suffix here. NetCDF is or HDF5 is actually a variety of NetCDF. So NetCDF actually has a higher amount of requirements to be compatible, and the ARIA GUNWs are in compliance with the NetCDF formatting requirements, and that's why they use a .nc suffix. So if you're going to download, it's the same as for downloading Sentinel-1 data. It uses the netrc file. It's coming from your regular Earth data login. The ARIA tools processing gets its DEMs from the open topography. So that's why you need this open topography API key installed in your .topo API. There's some plotting subroutines here. This is the it seems like the map got broken here. I don't know what happened to the link. Anyway, so as I mentioned, the GUNW files are in the Earth data system, and they're searchable at the ASF DAC. You can also use you can download them directly from the DAC, but there's also a tool built into ARIA tools that's called ARIA Download. So if you didn't use the stage data and you want to download your own specific data set, you just run ARIA download. You specify the track number that you want. W is the product output products directory. And this particular command only downloads this one interferogram, one pair, and it gets version 3.0.1. So because we use the pre-staged products that are already here, as I mentioned, it has these two files. And this gives more explanation about the file names. And those files are stored in this products directory. So ARIA Extract is a tool for once you've downloaded the data for looking at the layers and making sure that they have what you want. And has a bunch of options for doing this. You have to specify what products you want to extract the information from with the -F option. You have to tell it which layers. Remember, we have a number of different layers inside the file. You have to tell it which layers you want to extract. Or you can use -L all to extract all the layers. The ARIA Tools has this automatic download option. -D download will automatically go to Open Topography and try to download the Copernicus 90-meter DEM. That requires that you have your Open Topography API key set up. It also can download a water body mask. In this case, it's using a different water body mask than the one that we talked about earlier. In ICE2, there's the water body data set from SRTM. This is a different data set that's called the Globally Self-Consistent Hierarchical High-Resolution Geography data set. And that it's just another water body data set. You can also get a mask from your own special location by specifying. You can also, so one of the things that this can do is combine or the scenes. In this case, I downloaded 2 frames of the same interferogram. We have, you can notice that the dates are the same and only this time is different by 26 seconds. That means that they're 2 adjacent frames. We want to stitch those together. That's what this, what the ARIA Extract can do. That's, and we can specify a bounding box for cropping out a subset of we don't want to work with the whole data set. And that bounding box could be crossing the frame boundaries because it'll stitch them together and then do the cropping. So that's this minnow. Some of these other options are less useful. You do have to specify what directory you want to write the output products into. So there's different ways to use this. One of the one of the tricks that's been used for these geometry layers is they're not actually present inside the file at the full resolution. They're in the file because the incidence angle varies very smoothly across the screen. There's no point in saving the actual incidence angle at every pixel. It gives the incidence angle at some widely spaced locations, and then it does an interpolation. So the same technique is going to be used for the ARIA, the NISAR GUNW files. It's a way to save a lot of file space and really not lose any information. But you need to use one of these tools like ARIA tools to reconstruct the actual incidence angle, perpendicular baseline, etc., for each pixel because they're stored in these data cubes. And then combined with the DEM to extract them. Probably don't have time to go into a lot of explanation for how that particular part of the processing works. But then we'll go down here and look at the actual product. So we run ARIA extract with -F the products, and we're telling it to just look in the products directory and use all the .nc files. So it goes through and it sees that there's these two products. We didn't specify a bounding box, so it says that they specify the bounding box because we didn't limit to a bounding box. But once it's run through looked at those two files, then it calculates what's the bounding box for the two products and makes a new bounding box for the whole two frames. And it also, you can use this shape util function to see the bounding box with the coastline. So in this case, the bounding box covers the whole big island of Hawaii. And that's the area. So then the next thing you could extract the layer amplitude. The amplitude, this is the amplitude image. You can see there's a little bit of a line here where the two amplitude images got stitched together. You can look at the coherence. That's the stitched coherence. Note that the coherence layer that's in the ARIA tools is a filtered coherence. So this is the effective coherence that's calculated after the phase filtering. So it's a very smooth version of the coherence, and it's useful for phase unwrapping, but it's not useful for doing any studies of the actual surface conditions. And then the incidence angle. This wasn't working. This is not working right. So I'm afraid this part of the notebook doesn't work right. We weren't able to figure out why that wasn't working. It also downloads the DEM and does a lot of other things. So I don't want to spend people can go through this and you can skip past it's for some reason it doesn't extract the incidence angle correctly. Didn't figure out why that is. It does work for the other data sets. Selected cell and all below. No, this one isn't working either. That's a water layer. So there's another notebook here that's called ARIA TS Setup. So if you go back to the top level here, so this is it's a very similar program it's also part of ARIA tools. It's very similar to ARIA extract, but it has this is what we use. It processes the set of interferograms to specifically set up the time series of products to be loaded into MintPy. So I've already pre-run this over here in the test directory on my computer, and it's here. So this also has a stage data set. This is a data set over California instead of Hawaii. There's a larger number of scenes. This first part is all the same as for the ARIA extract notebook. Same download options. Some of these options are a little bit different. but we still have to specify the layers that we want to extract to put in. And you can do an additional multi-looking, and you still need to download the DEM and the mask. For some reason, those work with this notebook, they don't work with that other ARIA extract notebook. So I spent a day or two working on this. I couldn't figure out what to do, but so we're just going to go directly to the ARIA TS setup. So ARIA TS setup, we specify the products that we want to use. It's all the products that are now in this products directory. In this case, there's a whole stack of products, not just two. We specify the bounding box. This is the area of Eastern California. There's a minimum overlap. That's just specifying that we only want to use data where there's enough coverage from the ARIA products. We specify that we want to download the DEM, we want to download the mask, and it has this option to use multiple threads. And that on a computer that has multiple CPUs, it can run much faster that way by running parallel processes or threads on your computer. And in this case, so the standard layers are, it basically will always download the unwrap phase and the coherence that are always used, but then there's these additional layers. So some of the additional layers are a solid Earth tide calculation. So ARIA for the S1 GUNW has calculated a solid Earth tide using a model for the solid Earth tides. That's a kind of a long wavelength deformation of the Earth. That will also be available in our ISCE GUNW files. It includes a tropospheric estimate. This is for North America. The tropospheric estimate comes from the NOAA HRRR files. So it's the high rate rapid refresh NOAA weather models. And it also includes an ionosphere estimate. The ionosphere estimate that's derived from split spectrum with from the Sentinel-1 data. It's because it's C-band, the split spectrum is not always effective, so it's not as it may or may not be helpful, but we put that layer in there because to make it much more similar to the ionosphere layer that's going to be included with the ISCE GUNW files. So in this case, it's downloaded it and extracted the layers. So this is the mask. It's
Eric,
yeah.
There's a short question about the ARIA product tropospheric delay layer. So it's like,
Yes.
does the new version of the ARIA product include tropospheric delay from era 5? You said her, but
over North America, it uses HRR.
Yep.
In other parts of the world, I think it uses ERA5. This NOAA weather model only gets generated over North America, so yeah. The other thing is that it's actually encoded into the file as it doesn't give you the difference in the troposphere. It actually provides you both the troposphere of the reference date and a troposphere of the secondary date separately. So you can do the differencing later if you want. This is the mask, so maybe now you can recognize where this area is. This is the San Francisco Bay. That's a very famous shape that remote sensing people see very often. So we can see this is the water mask for San Francisco Bay Area, and that's the area of this particular stack. This is a plot of one of the interferograms. It's in the stack. This is from 2019, January 21st to 2019, January 9th. That's a 12-day interferogram. And it's been converted to meters for this plot. That's why it's labeled as deformation rather than radians. You can view that the DEM it downloads this Copernicus DEM. It's called GLO 90. That's a global 90-meter resolution DEM that's available from Copernicus and from Open Topography. And that's what the DEM looks like. It also generates this directory called stack, and in that stack directory, it writes out one file that's called the unwrapped stack.vrt. And if you look at that unwrapped stack.vrt, it's a virtual file that then contains a list of all the interferograms in that unwrapped phase files in that stack. In this case, there's 94 interferograms. And you can also get more information about the metadata for each one of these layers, each interferogram. That may or may not be useful. So we can also plot these layers directly from that stack VRT file instead of going back to the separate files. And so this is then the set of files that you can load into MintPy. MintPy will then will use this unwrapped stack.vrt. The solid earth tide, SET is solid earth tide stack. There's an ionosphere stack. There's a connected components stack, and there's a coherent stack. So these VRTs are basically a single file that contains the sort of pointers to the list of files. So there's actually separate files for each one of these that were extracted from the ARIA products, the GONW products. Where's the unwrapped phase? Unwrapped phase here at the top. You can also look at, so this is a big directory that has all the unwrapped phase files, but it also creates that virtual file that has that whole list in it. So this is a quick introduction to the ARIA tools products. There's another directory here that's the troposphere corrections. It's called HRRR, HRRR for the high rate rapid refresh from NOAA. And then, so each one of these is it actually makes a VRT file for each pair. But that's it actually does the subtraction because MintPy will look at it expects to have the interferogram, the tropospheric phase separated out. I mean, calculated as the difference for each pair. But it's actually stored in the ARIA GONW files as the separate things and ARIA tools is just doing the subtraction for you in order to make it more compatible with MintPy. And you'll be hearing more about MintPy on Friday. So I think we can also take a quick look at the ASF tools. They have the where's the so if you do a search for ARIA, I mean the Sentinel, the original raw Sentinel-1 data, you can go down here and select a bunch of scenes. And you can press this button called SBAS. So SBAS is that small baseline subset analysis, and this is just a tool to see the distribution of perpendicular baselines that are available for this particular frame over Los Angeles. And we can see that the Sentinel-1 baselines have been incredibly stable for a long time, but they started to diverge a little bit in the last year. A Sentinel-1 satellite is getting very old. It's been in space for 11 years. They're getting low on fuel. They're not adjusting the orbit as strongly now as they used to. So in general, you're going to see that the baselines are short up until about the last year or so, and then they've started to increase. Some of these pairs are over 400 meters, and that's probably too long. You want to have your, for SBAS, you want short baselines, probably less than 150 meters. So you can go down here and set your maximum baseline to 150 meters. If we do that, then, or 200 meters, then it's going to drop out these scenes that were acquired too far away from the rest of them. And then you can, if you want, you can ask them to do the Hype 3 gamma processing by pressing this button. I'm not going to do that now. We have 500. It's now estimated that it would do 532 pairs. It's doing, in this particular case, the default is it's only doing pairs up to 12 days. We can set the slider here to pairs up to 24 days. Now it would need to do 1,059 pairs to cover this area over the whole time interval. That's a lot of pairs. So that's why I think Franz can maybe explain more about what's the quota system for processing with the Hype 3 at ASF. You're only allowed to process a certain number of scenes per month or pairs per month.
Yeah, everybody that has an account gets 10,000 credits. And for like, if you do a burst-based interferogram, that costs a single credit. And depending sort of what kind of processing you do, it may either be a single credit or several credits, if that makes sense. Like a 10-meter full frame interferogram costs more credits than a 30-meter full frame interferogram. So I can't tell you exactly how many products you'll get. It depend a little bit on the types of product you're ordering. But for say, if you do a burst-based interferogram, you could order 10,000 interferograms per month. So the quota resets at the end of every month.
Great. So that's a quick introduction to the ASF Hype 3 gamma processing. There's also, so that's another option if you want to look in an area that's not the not available from the ARIA GUNWs. You can also search by this burst. That's what Franz was saying. You can request the processing on a burst basis instead of getting the whole scene through the Hype 3 system. The Hype 3 burst processing is actually done with ICE2, right? It's only the full frames that are done with the gamma. Is that right?
That is correct.
Yeah. So it's they've added this burst processing as a new service, so it's a new thing that it uses ICE2. The ARIA GUNWs are stored in the Earth data system, so we can search for them here. Soon, in another month or 2 months, they're going to see a ISAR option here for your search. So get ready for ISAR. And I think that's my 50 minutes. Thank you.
Thank you, Eric. Yeah, we are done. It's probably time for another break. Come back at 1 p.m. Pacific. Maybe those on the West Coast could grab some lunch. Very briefly. See you at 1. So the next thing on the agenda is atmosphere corrections.
Everybody had enough coffee?
I had two bites of my lunch. 2 bites of lunch.
It's never enough coffee.
My camera off. And eat. Anne, yes, the floor is yours.
Yeah. Well, let me share my screen. So welcome back. And this section is about tropospheric noise and ionospheric noise correction. And this 15-minute session will consider first a short lecture, and the lecture slides are available already on GitHub. And after the lecture, we will use Gecko's correction as an example of how you'll be able to apply a particular correction layer to interferogram. And the homework for this section is to run the notebook and kind of go through the material, as well as if you're interested, you can also try to apply Gecko's correction over an area that you're interested in. So let's get started. And let me first share my slide. Can everyone see it?
Yes, we can. Not presentation mode, but we see PowerPoint.
Slideshow from start. Okay, so also I would like to acknowledge that while I'm giving this lecture today, all the lecture slides and Jupyter Notebook are work that build upon many of my colleagues. So I would like to acknowledge them at the beginning of the lecture. Harash Fahati, Eric Fielding, David Baker, Simran and Shankar, and Roger McLeodius, and David Samuel. They made a part of the slide, so I'm just using these good informative slide. So at the beginning of the lecture, I would like to have a quiz. And here we have learned how to use ICE to process some of the interferograms. So here's a few sample interferogram, and that's over San Andreas fault. And so the question is, where are the tectonic signals? So, and if I are paying attention here, there is a temporal baseline that marked on each of the interferogram. So for this area, for the San Andreas fault system, based on the GPS information, we kind of expect about a line of sight deformation of 1 centimeter over a year. And recall that for Sentinel-1, each of the phase fringe of 2 pi correspond to 28 millimeter, that's 2.8 centimeter of deformation. So the true surface deformation over the time span of a year should be much less than a phase cycle. However, in most of those interferogram, we see many multiple fringes, and sometimes it can be a lot of fringes, and so clearly the answer is none of those phase signature we see here are due to true signal. And that's kind of the reason we kind of brought up in the time series inversion class earlier that the issue is when the signal we're interested in, typically millimeter to centimeter, they're very small. And when we're performing this time series S-pass inversion, we should be aware of those large scaled signals. And when I first started to learn about InSAR, so I find it's very, very useful actually after you process the data instead of just feeding them into an inversion framework. It's good to just there are some afternoon I just flip through all the interferogram over the area I'm interested in and see what they look like, and that gives you kind of idea about what are in your interferogram beside your signal and what are their spatial or temporal characteristics and what's their magnitude. So these are good information to have in mind when you're trying to solve the deformation signal. And sometimes you might have some creativity to design something that will be able to better separate these two. So let's first take a look at the very first 2-year interferogram. So there, I would usually say this is actually reasonably good looking interferogram. There's a few fringes that are across the interferogram. So if I was showing earlier for ALOS interferogram, I would say some of those ramp are usually related with orbital errors. But usually Sentinel data has a pretty good orbital control, so I see less of issue with the orbit. Some other thing like a tropospheric noise sometimes can also lead to these kind of ramp-like signals across the image. So the second image, you see these little almost like wave-like structures, and so these are, I see these kind of interferogram once in a while in various conditions. So these are actually related with the gravity waves in the troposphere that shows all those isolations. And in the 36-day interferogram, it's a pretty short temporal baseline for those long-term secular motion. Usually you don't really accumulate a detectable signal within this short amount of time. However, you see a lot of fringes in certain part of the interferogram, and they're fairly dense. So usually if you can have a comparison with the topography map at the bottom, and you can see these high fringes are usually concentrated in area where you have like a lot of mountains with a huge topography, elevation change, and so it is likely. So usually this is just our speculation based on experiment. In order to validate that, typically you need some additional auxiliary validate information, for example, maybe from GPS signal, Venice delay estimates, or some other information, weather model. But it's very likely these topography related fringes are related with maybe stratified tropospheric noise. And so for the bottom interferogram, this 24-day interferogram, again, it looks quite nice. And so one thing you can see is that there are some kind of low, like a long wavelength signal. And one thing I can kind of understand it's not a real signal. It's like usually if you have a tectonic, like a fault motion related deformation signal, they would correlate very strongly with the fault, and they should be very consistent. But if you have a tropospheric ramp or like orbital error, so from interferogram to interferogram, this ramp orientation typically gonna looks different from things to things. So overall, other than that, what you could notice is there's some kind of a decorrelation we talked about a little bit earlier in this mountainous region. So one possible reason is sometimes you see this kind of decorrelation in mountain region. You should go kind of just check the data acquisition date. So if you have a snow-free day from another snow day, so the surface scattering properties is considered as a dramatic change of the surface, and that leads to decorrelation. So snow really was decorrelation. So if you work in cold region, like in high mountains or in the Arctic region where snowfall is common, so you will sometimes have to be aware and only use those snow-free days for the analysis. So usually the no snow versus snow day, usually their phase quality gonna be heavily decorrelated. And then we have this last 3-year interferogram. So usually for this secular motion, 3-year should give you a about a phase cycle. I mentioned a year, 1 centimeter of motion. However, you still see multiple fringes that is beyond what we expected from this area of interest. So what this can be, it can be maybe some tropospheric noise, but perhaps also with ionospheric noise. So, and towards the later part of the session, we will give a little bit of distinction. How do you know it is from tropospheric noise? How do you know it is from ionospheric noise? So, so given that these noise are not small numbers, right? And so how are we going to mitigate them? So the key idea is sometimes we can use auxiliary data when it's available, and also based on every time when you're using some data, we have to understand its limitation and their underlying assumption. And also, I think another key idea is depending on the noise, their temporal and spatial characteristic should be somehow different from your true deformation signal. If they look the same temporally and spatially, then I don't think they're going to be a very easy way to separate them, right? So hopefully they're different in certain domain, and so that allows us to be able to separate them in that domain. And so also among those fringes, other than this decorrelation noise that is spatially incoherent, the tropospheric noise, all those ramp-like signal, all the ionospheric noise, they are spatially coherent, just like the deformation features. So these PS analysis, spatial filtering, all the phase linking approach. So their essential goal is to enhance the coherence, to get rid of this spatially incoherent decorrelated pixel. So once these are mitigated correctly, this approach won't be able to separate the tropospheric noise, all those spatially coherent noise from the deformation signal. And here is the center of this study is on how you can mitigate the tropospheric noise versus ionospheric noise, and through maybe auxiliary data correction and also time series analysis. So let's move on. So what is troposphere? And so it's very important to know the radar wave are refracted. So as the radar microwave travel along the Earth's troposphere, it will add a little bit of a delay to your range measurement. And so how much of this delay is going to be? So is depending on the pressure, the temperature, and the amount of water vapor. And in some area where, for example, you might have a strong monsoon pattern and you have a very distinct wet season or dry season, and then the tropospheric noise characteristic might even have a seasonal pattern associated with that. And so here is what I show as a tropospheric noise. And I recall Scott once told me, because his work was heavily focused on tropospheric noise, we were working on a West Texas study when there's very hot summers, the tropospheric noise typically is pretty severe. And so when he was looking at this cloud on the sky, all he can imagine at some point, because the PhD study really break people, is that they think about all those fringes he saw in those Sentinel-1 interferograms. And so for this tropospheric noise characteristic, there is a very important key here is that it's frequency independent. So you will see the same amount of delay for the X-band sensor and L-band sensor. And it is usually more severe if you have a hot, humid environment with large elevation change. And so if you have a flat, very dry, arid region, usually it's going to be a smaller magnitude. So the expected tropospheric noise is going to be kind of depending on the region, but they're in all the wavelengths. Just the switching from L-band to X-band won't help. And also for a particular site, and typically it's going to have some certain characteristic following the climate pattern. And another important thing to kind of recall is that the InSAR phase measures the phase difference between two SAR acquisitions. So here we have this two, the Sentinel-1 data that are flying over the same area at a slightly different location, a TI and a TJ, right? And so, and at the pixel Q, you measure the the difference, the range difference between these two blue paths, which is the phase difference related to, and in this path P, you measure the phase difference between these two orange paths. So InSAR is a relative motion. So you measure relative motion between pixels, and usually we use a reference pixel. So it's important to know while this delay is big, and given that these two satellites are very close to each other, so most of the delay among these two passes, differential, this double difference is similar, right? And so it's only the difference of the tropospheric delay between the blue path and the orange path. So it's a double difference here that matters. That said, although the tropospheric noise, absolute tropospheric noise can be big, the tropospheric noise that matters to the interferogram kind of depending on how big you are, the site is. So for this area, if this P and Q is very close to together, maybe 100 meters apart, then they're essentially the paths that from the satellite to this 2 pixel are essentially the same. And in this case, when you're doing this double difference, this delay is canceled. So, but if you're working on a big sentinel scene with each of the image of 250 kilometer by 250 kilometer, and you can see the tropospheric delay that they see at this further away pixels can be a lot more severe, right? And so that's why for the larger scale analysis, you would anticipate a much larger residual noise in your solutions. So in order to mitigate them, I think it's very important to know the characteristic of the tropospheric noise. So when I started, I listed a very informative reference here, 2003 reference that I found that gave me a lot of physical intuition, and I'm listing 3 key results from that paper. So essentially what this paper does is that's kind of still like an early stage of InSAR when people start to look into the interferogram and they notice these fringes and they want to better understand what the tropospheric feature looks like. Then what they did is they went to South California where there is a very dense GPS network. So at every GPS location, not only you can record the east, north, and up deformation time series, you can also get an estimation of the tropospheric delay, zenith delay, based on this GPS measurement. So what this study does is they compare the zenith delay at like two different delay at 2 different stations with various like distance and at a different time. And so, and here are some of the key results they got. So the very first one is telling us a little bit more about how the temporal characteristic of the tropospheric delay. So the SIN line is at 2 stations recorded at 244 kilometers apart, and the SIC line is at a 2 station that is recorded at 20 kilometers apart. But they kind of shows a very similar, like you can see this feature, the structure function flatten out after a day for this both distance. So what you can see here is essentially what this means is tropospheric noise become uncorrelated after a day. And given that InSAR data, earlier data usually acquire a new acquisition every 35 days to 46 days, even for Sentinel, the shortest time interval is every 6 days, and NISAR will be 12 days, and which means essentially for the tropospheric noise that you expected from each of the SAR acquisition, you can consider them as temporarily random. That's why in my time series simulation, those blue stars, I just randomly scattered around from the true surface deformation. And another implication is that if you would like to develop some model to correct the tropospheric noise, ideally you would like to have a tropospheric noise measurement, like estimate around the same time as the radar acquisition, because these things change dramatically. Like today it's raining versus tomorrow it's not going to rain. They don't correlate that strongly, right? And so, so that's why you would like to have a like basically simultaneous measurement of the tropospheric noise in order to do really, really good correction, right? And so unfortunately we don't have that available. That's why these our lot of the tropospheric noise correction layer was listed as optional. We can try it, but you don't want to take it for granted. So because of this limitation. So for example, if you're using some weather model correction, a common temporal resolution is every 6 hours. And you can see from this curve, things already become a little bit of uncorrelated. And that's why later in this Geico's correction notebook, they ask you to tell them the exact time the SAR data was acquired, because that's actually an important piece of information needed to get the most close possible data or model output that is close to the SAR acquisition. So that's the very first characteristic. So the second characteristic of this panel B is about the tropospheric variance as your like two GPS station grow further apart. And I would like to remind people here the plot is on log scale, kind of remind to the earlier slide, like if you have 2 pixels, basically what it says, then the tropospheric noise can be very small. But if you go to like a further away pixels, then those the tropospheric noise between these 2 pixels can be much larger. So this is a case for Southern California, which I consider as a moderate tropospheric noise cases. Like usually if you're going to a tropical island, it's going to be a lot worse than this. But for this case of California, it's a moderate tropospheric noise. And based on what they find is if you have a small site that is like just a kilometer, then the expected tropospheric noise is only about 8 millimeters, so which is not too bad, right? If you are really looking at a localized area, zoomed inside and looking at the relative deformation, localized deformation. But if you're moving towards a much larger area, typical to a sentinel scene, right, hundreds of kilometers, then you would expect a centimeter or more tropospheric noise in your result. And the third one is about the height differences. And you could see that earlier we see there is sometimes you see this larger tropospheric noise in this mountainous area because if you have a very tall mountain, even just the path from the satellite to the top of the mountain and to the bottom of the foothill of the mountain would be very different. And of course, they're going to add a different delay. So usually you will see a height dependence on the tropospheric noise. So that's what we call the stratified component. And however, I do want to notice that you can see, well, there was a topography dependent component. The spread is also quite big. That also reflected there is a turbulence nature that is somehow random and evolve rapidly and often not correlate with topography, and both can happen. And so here is a summary of this kind of 2 tropospheric noise. And what you can see from the top is the stratified component. Typically, it is based on the topography plus the pressure and the temperature model. And the weather model usually will be able to predict what's the expected tropospheric noise over this area and what's the difference between multiple paths. And what I have found is because it is correlates with topography, it is also somewhat predictable, right? And so if I look at Kilauea and the Mauna Loa, always tend to have almost like a contour-like feature near the around the peak. So that's why I find that usually if you have a weather model-based correction and for this area with a steep topography, usually they can do a fairly good job to capture this stratified component. And one way to kind of mitigate that, the weather model has a usually poor spatial resolution, definitely not at a meter level, tens of meter level that the InSAR pixel are, but they're usually at a kilometer or longer spatial resolution and the temporal resolution. So in area with a very dense GPS network where you have this zenith delay estimate, high quality measurement, then when merge the GPS measurement and the GPS zenith delay estimate, I think you can have a fairly good chance to remove a lot of this stratified component. However, in a lot of the cases, if your area is fairly flat, and if you look at the interferogram from days to day, you just kind of randomly see these weird fringes pop up here and here and there, and it doesn't seem to have anything to do with your like maybe a fault-related deformation or like a stable on the top of a deforming aquifer. They just kind of coherent blobs that shows up, just like sometimes the clouds can show up in any random location. So those are usually those turbulent tropospheric noise delays. And some of these features can be fairly localized, like at a kilometer scale, and also pretty random in time. This is based on sometimes I look at them. And so if this is your dominant noise, then what I have found is these existing weather model based correction is not going to be very reliable, and you would have to feed this into time series, perhaps employ temporal filtering, because you recall that these kind of turbulent noise are uncorrelated in time, so they tend to jump around in the time series. And hopefully, if you have a very noisy time series derived, there are ways to do some kind of model fitting to remove some of those jumps and get the internal trend, or maybe a transient signal. So uncorrelating time, a key idea is almost unpredictable. And what I have found is if you're implying a spatial filtering, these turbulence noise also are not always successful, just because of their spectrum overlap with the signal by quite a lot. And if they share the common band, then the filtering won't be able to, frequency filtering won't help. So the atmospheric correction, what are our options? And so the first option is somehow based on weather models and also the existing GNSS network, and our Jupyter notebook will provide an exercise to incorporate these like Gecko's correction layer that is derived from weather model topography and GNSS data, and for a case study. So it's very important to kind of keep in mind that they might not have enough accuracy or temporal spatial resolution to ensure always to be successful. And one way we can kind of experiment is that if like you generate a Gecko's correction layer for a particular interferogram, they look just like a lot of the features in your interferogram, and it's very likely the Gecko's correction is needed, because Gecko's doesn't know what the interferogram should look like. They are just based on the weather model, and if they can predict what you actually see in the interferogram, so likely in this side, these kind of correction will be beneficial. And if you don't see much change, so you can kind of decide whether they have a substantial impact on your time series analysis. In the case you don't want to apply Gecko's correction, is that you find the Gecko's like a prediction predict a pattern that is not seen in your original interferogram. So not only maybe it didn't remove some of the features in your interferogram, to add some additional feature that was not there before, right? And so in that case, that you shouldn't apply this correction. So so usually encourage you to visualize it, and for a case-based study, usually with the area with a lot of stratified component, these models are very beneficial. So the second option is through filtering in both time and space. Although I find the space is only useful for removing this very long wavelength scale tropospheric noise, but those localized turbulence noise are just they are too similar to the deformation signals, and so so it's a kind of a good important to remember. You can try different type of filtering, and then but you want to keep in mind any filtering. They don't know what are signal, what are noise, and if they look too similar in time or in space, then you might remove the signals as well. And another alternative I think you might try to do is like earlier in the early stage of InSAR, and if you assume you already corrected those stratified component of tropospheric noise, so most of them are those random tropospheric noise, right? In the earlier stage, you have data every 46 days for the ALOS-1 data set. And so you don't have a lot of measurement within a year, and we do the deformation analysis with that, right? And it's gonna limit it. Sometimes it's very challenging to reach millimeter level accuracy, but it still doesn't preventing you from doing analysis. Now we have, with the advantage of using Sentinel-1 data, you sometimes have data every 6 days or every 12 days. it's a good idea to use all of these data, right? But then you can also subset them to say, I only want to use all the acquisitions every 24 days. And then in this way, you have a two subset of the data. And keep in mind that because of this temporal characteristic, the deformation signal, if this is a long-term secular motion, both data sets should contain similar signal or very similar signal, but their tropospheric noise is completely different. So by performing the data using all the SAR acquisition and using only half of the randomly selected acquisition and then try to compare with the other, it also kind of give you an idea about what's the residual noise impact based on the difference of this solution. So those are a kind of approach. We used to not be able to do that because you only have a 10 acquisition, you've got to use all of them. But now if you have hundreds of acquisitions, so you might be able to afford to split them into half and then perform an independent analysis as if the data was acquired every 24 days. It's still much better than those 90s data, right? And so the third one would be trying to directly remove a topography correlated model. So if you, I think this option sometimes is going to produce a similar effect as these weather models, because the weather models, they usually, when they predict the delay, they kind of take into account of the topography and its impact on atmospheric pressure and water vapor. So you can also just directly remove, like based on the data-driven approach for an area and trying to find the correlation of your phase with the DEM at every pixel and then remove that. The danger here is you need to have some prior information that your deformation signal is not really with topography. And in this case, otherwise, some of the hydrology signal might be related with topography, and the third approach might, again, remove both. So those are some correction approach that is available for tropospheric noise correction. And now we're gonna move to the ionosphere delay correction. So what's the ionosphere delay correction? So it's essentially is due to the total electron content in the Earth's plasma layer, and so the difference between the ionospheric noise delay and the tropospheric noise delay is that the tropospheric noise delay is gonna impose the same amount of delay in all the radar wavelengths, but for the ionosphere delay, it is depending on your radar wavelength. So here, the TEC is a total electron content is an integrated total electron along with your radar like propagation path. And here you have an inverse proportional to frequency squared, right? And so the frequency is 1. So this means based on this relationship, if you have the L-band data and you have an X-band data, the impact on the L-band data is going to be a lot worse. So this kind of a delay is a lot worse. And here is a map of the global TEC map, and it's updated every 2 hours. Again, so only you can kind of using this delay map kind of to delay a correction layer. We're going to talk about that later, but again, it might not have enough temporal and spatial resolution to capture what is happening at that right amount of time. And another key idea here is when you're looking at this kind of a correction, and usually you will find that the ionosphere noise usually worse in the lower latitude and also the Arctic region. So in the mid-latitude region, the impact is typically, especially if you're talking about C-band, is going to be fairly minimum. So it's not a required correction for a lot of the cases. And so, but if it is the case, you will definitely notice that. And another idea is not only it kind of depending on the wavelengths you're using and the region you're looking at, it also has a cycle that really was the 11-year solar cycle. So you can see as ISCE is launching, we're gonna go towards the peak of the solar cycle. So we're gonna definitely, and it's the L-band 24 centimeter. So we're gonna definitely notice this kind of artifact more in the upcoming ISCE data. And so give you a reference. So my very first project was actually on Ionosphere, right? But around that time is about 2010. So even with the L-band data, after I learned about it, in the actual data analysis, and I just never needed to perform the correction for a while. So in the Arctic region, I did notice a very severe ionosphere effect, but at that time, it only impacted a small subset of this data, and they have a very distinct pattern because they look like these azimuth strikes. And so I got lazy, I managed to throw them away, and I still got enough of the measurement and be able to perform the analysis. Then after the Sentinel-1 was launched, so in some of the data in the low latitude region, I start to see like a lot of those cases, people do need to worry about that. And so, and right now, I think we are relatively, like in the past couple of years, I haven't seen any signatures for the Sentinel data that are quite over this time for the mid-latitude region, but I do see some artifacts in the high, like Arctic region. So, but luckily, even when this can be a very severe aspect, then I usually leave the tropospheric noise there, let the time series analysis to correct for it. But I have to throw away some of the ALOS pulsar things because the noise is just overwhelming. It's several cycles of the radar wavelengths, and unless like and it's just gonna become the dominant feature in my results. But luckily, for the upcoming time, we actually over time we have an algorithm that is mature enough to be able to correct for that. So let's go over that. And for NISAR, they are based on this algorithm, so they are going to provide a correction layer. So hopefully, even its L band is going to come into a active solar cycle, we won't have to worry about this. Is not going to be the limiting factor. We can predict it, and hopefully we can reliably correct for that. So one of the important idea is that an important idea, and this is actually not just first applied for InSAR, it's in GPS data. So for GPS, they have a dual frequency measurement. So as they go through the ionosphere, the amount of delay is going to be different for these two frequency. And everything else, for example, the range measurement, the tropospheric noise delay are the same. So when you have these two measurements from the satellite to the ground receiver at the same time along the same path, right? And then you could just calculate their difference. And if the ionosphere is the only thing that's going to make a difference, then you can, based on this difference delay recorded in this two frequency and by proper scale by this relationship, and then rederive what the ionosphere attack is, and then correct for this ionosphere delay for each of the frequency band. So that's kind of the same idea. It's just the GPS, you do it in 1D, and for radar, you have to do it for every single pixel. So here what we are showing how this can be done. So this is your full radar bandwidth of a spectrum, and through a bandpass filter, you could actually isolate this spectrum into a lower band and a higher band, and then do a IFFT to translate it back into the time domain. And so instead of just having a single interferogram, now you could form a high band interferogram using this high band only, and then this low frequency band only. And the key difference, they were quite at the same time, everything's different, but this two band has a different center frequency. And that's why for this two interferogram, their ionospheric delay is going to be different. And thus, by combining this two phase difference, and there is an equation, shows here, well, allows you to be able to predict the ionospheric phase and then enable you to do the correction. And here is an example. And this is why I mentioned if you don't correct for it when you notice the ionosphere, and you either throw it away or you correct for it, right? And so there are many wavelength cycles of signal, usually very striking meter level delay is possible. And so this is a full band interferogram and a low band and high band interferogram. So first looking, because other than the ionosphere delay, they look the same, right? So they don't look that different. But after you do this difference through this calculation, and you get something looks very noisy. But you push it into a low pass filter, get rid of those high frequency noise, then suddenly you start to have this correction layer that you could apply to the original interferogram. So the difference between the full band and the ionophoric layer is going to be hopefully ionophoric corrected interferogram. So the question here is why the result without the low pass filter is so noisy. The idea is in order to make this correction successful, ideally, you would like to have this FL and FH to be as far away as possible. Otherwise, the difference would be so tiny. And then if you have any small noise in your measurement, then that would blow up and make your result unreliable, right? And so ideally, this only works so well if you have a larger separation, which is like why GPS, when they have this dual frequency, they designed so that the FL and FH is so different that the correction can be done reliably. But unfortunately, for Sentinel data, this frequency difference is not very big. And that is why this ionophoric correction is optionally, because it doesn't always work. It requires you to try it, and it works great sometimes, but it can fail in some other time. And that is why for the ISCE, so they trying to widen the bandwidth so that there's going to be a bigger separation so that we can perform this correction more reliably. And in the optional supplemental material, Harash developed a Jupyter notebook that kind of goes through every single step for the ionophoric correction, how to generate those kind of layer. And so that notebook can only run on the street map mode for like ALOS data. And that's why we moved it to supplementary, but it's still gonna be, because useful if you're curious how this kind of a correction can be done, to check that notebook, because it kind of doesn't matter which interferogram you're getting. Once you have the interferogram, this bandpass filtering and the correction, this algorithm works in a very similar way. And also later, I think Area also will try to publish a correction layer for the sample. This is going to be one of the standard product for Area that, so hopefully you could just take that and apply that to the interferogram directly, but just cautious for the Sentinel-1. It doesn't work very well. Doesn't mean the algorithm doesn't work. It's just the separation of FH and FL is too small to make this correction reliable. So here is another example. So this is the original interferogram that contains a co-seismic deformation, but unfortunately there are many other fringes, and so after you are using the split band spectral method, this is the estimated ionophoric delay. You know it's successful because when you are doing this difference, all the deformation was canceled. If you can still predict something based on the split spectrum method, that's must due to ionosphere, right? Because tropospheric noise in this kind of difference of these two interferogram, they're all canceled out in the same response. And so this is after correction, and you can start to see this nice co-seismic deformation fringes a little more nicely. So because it looks like they're kind of in a comparable way, so it's gonna really messed up the original interpretation without the correction. And here is another example for the correction for the ALOS 2 data. And so what you can see here is it can be pretty dense, right? But in some cases, if you don't have any correction layer available, and you can look at the interferogram. In this previous case, the ionophoric noise fringe pattern is somehow irregular, so you cannot really use a ramp removal to remove that. But for this particular case, if you look at the interferogram, I believe you can probably get something with comparable quality by just estimating a linear phase ramp and remove that, and then perhaps you can get something that is reasonably good. So this is the end of the lecture, and I'm going to unshare this and then go over the Jupyter notebook exercise. So later, if any of this correction layer is posted, and so the idea is kind of similarly, it doesn't matter whether it's a tropospheric layer or the ionosphere layer, and we should be able to using a very similar workflow to deal with that. And so let's go over that Jupyter notebook. I'm gonna share my screen. So this Jupyter notebook It's developed by David Bickert a few years ago, so I only made a very minimal change. And so it's kind of the same thing that will go over a geocoded interferogram and how do you apply the Gecko's correction to the geocoded interferogram that generated from the TOPS app mode. So the homework would be trying to run it, but one bonus question is if you're interested, you could also try to apply the same correction for your own interferogram. So this is roughly the area where the earthquake happened. And the initial part of the notebook is nothing more than just trying to set up the working directory on Alaska OpenSAR Lab, and as well as define a few plotting routine that later for you to visualize the data. So that's step 0 you should run. I already ran it, but I recommend you usually run one step at a time so you kind of know what were generated at every single step. So here, there's an option to use the pre-staged data, and that was generated from the TOPS mode, TOPS app.py. And so we have a pair of interferogram. So these are the 2 SAR acquisition date. And also they have the geometry information from the line of sight vector. And that will come in handy because those Gecko's correction are the predicted delay in the zenith direction. That's directly from the top down, right? But the radar is looking sideways, so you will need to account the path difference from this difference in the geometry. Right, and so then the section 1 is give a overview of the tutorial input data set. And so if you want to prepare your own run, you should try to make sure all those data were arranged in the same way. And so, so these are the data. And then the section 2 is about the Gecko's data set. So there is a reference for the Geckos on the website paper. But essentially, they're using weather model and with a GPS zenith delay estimate and through interpolation and generated this data product. It is an on-demand product. And here we go through how you can request and download the data over your area. And in the section 2.21, it went through some of the key information. So one thing, of course, you need to know the region, but usually if you're already plotting an interferogram, you know what you're looking for, right? And so your Gecko's region, you can kind of request it slightly larger than that, right? But it cannot be smaller because if you only correct a partial part of the pixel, it can be confusing, right? And so the region is okay. And one important thing is you on this website, you need to provide the date, but as well as the acquisition time for the data. So when you're trying to apply data for the same path due to its satellite orbit, usually if you're saying, oh, I'm acquiring data over this area, I'm interested from past like 78. And so as long as it's from the same path over the same area, that date is going to be more or less the same. And so that's how hopefully save you some effort. You don't have to check for every SAR acquisition. For a stack of data, you just need to check once. And in fact, this UTC time, when you download the data in the ESF data search archive, when you click on those zip files, they actually show that in this interactive window that where you show ascending path number, frame number. It also tells you the SAR acquisition time in terms of UTC. And also, after you download the data, you can see this very long, like a format for that data file. So this date is the data acquisition date, right? So this is what required for Geckos. And this digit right after is 1500. So this is the UTC time. And if you want to double check, you can verify that with Alaska. So this is just an easy way for you to get a UTC. And we also went through how do you figure this out through the data itself. And then the side note I want to mention is from the ascending and descending geometry, I believe one path is usually will arrive at like like at least that's the case for my area. So ascending data typically arrive like for my areas like in the late afternoon, and the descending data is like early morning, and that actually can make a difference in the expected tropospheric noise level for this area. So you might expect less noise in the early morning acquisition from the troposphere because it's quieter, the sun hasn't really shined on the land for a while, so it's not a lot of turbulence noise, right? And if you have acquisition from a path from the later afternoon, typically there is a little bit of expected magnitude difference between these two types. And after that, and we can request the data, and it's a pretty straightforward process. And so we, in this test data set, we already have the data requested, but you could just follow the instruction on the website, provide the information, and also download the data yourself. I try to download a pair. It only takes less than minutes for me to get the result, but if you have a larger data set, and that may take longer. And the third one, once you have those tropospheric noise correction, the geckos is gonna give you those tropospheric noise delay, absolute delays in meters, right? And so, and you have to convert them into the expected slant range phase along the radar line of sight direction by taking into this theta is the look angle that you can derive from the line of sight vector. And so the code I also mentioned, like when you download the data, there's a binary format and the GeoTIFF format for the Geico product. Either can work, but here we went through the default of the binary, and there are some instruction on what if you get a GeoTIFF, what you do as well. And after you have downloaded the data, correct them into the slant phase, and the next thing is the Geico's data was usually sampled in a different coordinates system. Even they're all on lat long, their spacing may be different, and they might not exactly capture the same areas, and you can use GDAL to do the resampling. And here is a preview of what those Geico's data looks like. So the first order you can see, if you plot the DEM map over the area, the Geico's prediction usually is gonna correlate pretty strongly with the topography, and that's why I mentioned usually if you have a strong stratified component, they might help. But if your noise doesn't seem to correlate with topography, then they might, and then you don't have a very dense GPS network to capture those localized pattern, then this correction might not help much. And so here is how we are doing the conversion. So those are the slant range delay for the two dates. And it's important to note is the relatively difference between these two acquisition between the pixels that matters, right? And so here is to calculate the difference phase delay on these 2 dates. And then basically after you calculate this phase layer, you apply to the original interferogram to have a before and after correction. And in this case, I think if you're looking at the profile, they made some change, but visually, perhaps because the deformation signal is already big enough, right? And so, and it doesn't make that much of a difference. So feel free to run through it and look at the code and let us know if you have any question. And for this ionosphere correction layer, because it is derived directly from the InSAR data, I don't think you have to apply those slant range correction like those tropospheric noise derived from weather models. And that's it. And I think I used up all the 50 minutes.
Great. Thank you. I think what remains, unless there are any questions out there.
There were some questions about geckos, and like there was an earlier question about how, I think Gareth may have answered that question, how geckos is different from just applying a weather model, like, you know, how it does things differently than just taking your ERA 5 data and converting it. So that was one of the questions.
I think there is a paper on the Gecko's website that kind of details their algorithm. So based on what I know, they don't just use the weather model, which is typically gonna be at like a 15-kilometer grid, and you look at those localized pattern. They need a higher resolution to capture those features. So I think Gecko's use a hybrid weather model plus all the GPS zenith delay estimate and interpolate between to kind of be able to capture those finer structure. But I think the area will also probably release a topographic tropo correction layer soon, based on my understanding. So there will be some various data product, perhaps based on different weather model. And so I think it's worth to try them to see if they predict consistency or not. But the details, I think we should check with their model because I'm a user for
I'm
their
not sure that
correction.
you get the GPS correction for in the standard results.
I believe I checked their paper. They claim they use some GPS data.
They do in those results, and they have a framework for incorporating them, but I don't think you get them unless you ask them personally very nicely. Then, if you're a friend of Zhenhong Li, he might actually process the GPS data part for you. But I think the standard product is just the weather model, but it uses their interpolator, not the which is different from other groups.
Yeah, and I do want to mention, although I mentioned about the limitation of the weather model, and these are the field also is rapidly advancing. So hopefully they're going to get better over time, and maybe they're going to be more effective.
There's a question now by Blanca or Bianca. Do you want to ask your question live?
Yes, can you hear me? Yeah.
Yes.
Yes.
Yeah. Well, it's about the Genesis. I don't know if possible, use the troposphere solution from Nevada Geodetic Laboratory to correct interference.
Sorry, there was could you repeat the question again? So there was a freeze on my side. Sorry about that.
Yes. It's about, it's possible use the tropospheric solution from Genesis Station at the Nevada Geodetic Laboratory to correct interference?
So you can give it a try. So when I was a student, I actually looked at, and it's also depending on the scale of the noise you're looking at. So I looked at the site, that was a long time ago. The Hawaii Big Island has a pretty dense network because it's an active volcano, they instrument that. And for that particular study, I find the InSAR derived deformation and also this feature are still not sufficient if you're just interpolating with like a 15 GPS stations over even a very small area. But I think it's better than nothing because after I derived the time theory, this unconstrained S-path, you're gonna see those variation in the tropospheric jumps in the time theory. They correlate very well with those GPS Venice delay estimate. But if you just interpolate through the GPS station, I don't think you can correct them just based on that alone for the site I worked on.
Thank you.
But they can probably improve, remove at least a portion of it if you have a dense network.
I feel like Eric was a co-author on a bunch of papers about this kind of thing, where you could try and estimate what the vertical gradient is from the different GNSS stations in an area, and then convolve that with the topography to get a higher resolution interpolated estimate. Yeah, those papers are like 20 years old.
Yeah, that was when Zhenhong Li was still a grad student.
Yeah, Lee and Fielding, there's a whole load of them. I think they're good still.
I also didn't get one up for today, but I was told by David to pitch the tropospheric product that's coming out. I was in a meeting, so sorry if I didn't hear if you've already mentioned this, but the HRES data was going to be a part of the opera displacement as like a layer, just like a layer you apply. That took really long, and instead we are now doing a global thing that you can apply to more than just the opera data, but you have to do the intersection with the DEM and get it to your study area. But it should be pretty easy to apply because it is basically Radar. The library has been applied, summed up, done the integration, and now you just have to intersect where the heights are at your study area and then you get the correction from ECMWF HRES data.
You want to explain what HRES is?
HRES is like ERA5, but higher res. And if you ask me to explain it further, I will defer to Marin. It's another model from the European Center for Climate and Weather Forecasting. And
yeah, it's higher spatial resolution. It's also higher temporal resolution. I think it's every hour.
That sounds good.
Okay. I think we have every 6 hours.
You might only use it every 6 hours.
The forecast is every hour. You're right. We have access to the reanalysis data, which is every 6.
Yeah.
Yeah, both atmospheric and ionosphere correction, as Anne also indicated, is still, sometimes a bit of handcrafting to get it right for every case. There's a lot of different atmospheric situations you may encounter. We looked in an office hour at a interferogram sample. In some places, atmospheric delay is quite severe, especially in places where it's warm and humid. Middle East, etc. There's many places where atmospheric delay is difficult to deal with. It is still I think I would say, major limitation, limiting the overall accuracy you can achieve with InSAR. And one approach to mitigate as much as you can is by using time series analysis and using redundancy to try to suppress as much of that noise as you can.
Right, you can make a time series that spans an earthquake and estimate the step in the time series, and sometimes that will remove a lot of the stuff that's not persistent in the time series. So the real deformation is the kind of the baseline around which the noise is perturbing it, and the more interferograms you have that cross the earthquake that you can use as redundant information, the better your chances of capturing that step and removing the noise. I forgot to answer that. People have been asking questions about, so how do you remove the turbulence? Well, basically you have 2 methods. That the time series method is one, but if you want to make a correction, really the only way is to use some other information that was collected at the same time, and there's not very much of that. GNSS would be one way, and there are a few imaging spectrometers that are sensitive to water vapor that you can use as a correction. The only problem with those is that they don't work where you have clouds, and there's often a quite high correlation between the presence of water vapor and the presence of clouds, so that's not great.
Yeah. And I want to also add for the time series analysis, the ability to mitigate the tropospheric noise is really typically you're trying to have a trade-off between the temporal resolution and the accuracy. And the 2 ways to separate these 2 is basically take advantage of the characteristic, the tropospheric noise on different satellite a day are uncorrelated. And so that if you have a long-term linear trend, if you have 3 years of data, yes, it's a very noisy time series, but you can detect a much smaller trend through noisy time series if you have a lot of those noisy measurements. So that's, but when you are detecting the trend, it doesn't mean you could achieve the similar level of accuracy at a 12-day resolution. But given the fact you have data every 6 days, so that you can better extract that trend over a long period of time. And an alternative way, without the sacrifice of temporal resolution, as what Darius mentioned, you could incorporate the deformation model for a step function. And if you know exactly where the earthquake is, and for large earthquake, you need a winding interferogram span the event. But if you find a winding interferogram looks like the noise is kind of you could also make another pair, and the more of those cross event pair you have, you can do a step function fit. You can also just do a simple average of these, and that's a kind of taking into accommodation event. There is a step like a signal at a given date. And similarly, if you have a seasonal signal and that these areas having an aquifer pumping, you could incorporate a seasonal deformation signal in your time series analysis. So this requires prior knowledge so that it can maybe even like just only choose those pairs that is summer, winter, where contain a very large seasonal deformation, and use all of these to try and better estimate that component.
Great. I have one more thing I have to do before we finish, so I will share my screen very briefly. Finish for the day, that is. And that is to show you what we have down for homework for you for today. There are two things. One is to complete the TS setup notebook that Eric demoed earlier, and upload proof of that to Moodle. And the other thing is to run the notebook that Anne just showed, and upload proof of that as well. Hopefully that's straightforward. Hopefully the GACOS website comes back up soon so that people can actually run things in it. If that continues to be
the administrators have just now upgraded everybody's storage to 250 gigabytes. So you need to turn off your server and then restart it, and then you'll have 250 gigabytes of space. If you don't, then you'll have enough space to actually run the ARIA TS setup notebook, which otherwise you'll run out of space even just having the TOPS app run from yesterday.
Of course, some of us deleted our interferograms from yesterday. But yes, okay. Good to know. Everyone who wants to up their space, turn off your notebook and turn it on again.
Shut down the server. Yeah.
Shut it down. And then you'll also, hopefully, when it pulls the new materials in, it will pull in also Anne and Scott's slides from earlier today.
I have a question.
Yes.
These assignments are due after the class or after the course?
You have a week after the course ends to complete
that's
everything.
Good. That's good. Thank you so much.
But do everything as soon as possible if you can, because you'll lose momentum and forget, and you won't be able to ask us any questions. We will not be nearly as responsive next week as we are this week to your questions on Slack or anywhere else. And we won't have office hours next week. And if that is all the questions, we almost finished on time today. That's because I wasn't talking, I think. We're much more efficient when I'm not involved.
There is one more in the Q&A from Camille.
I have an AWS. Would it be possible to get a copy of the image used to create the machines we're using? We have in the past offered a Docker container. We have not talked to the people at ASF about that, but it does exist. Some form of it exists. And if you don't have your own machine that you're comfortable using Conda on, that is one solution. I would say, though, it's not actually that difficult to install all these things on your own machine. If it's a Linux machine, particularly, that's quite easy. And even if you're using a Windows machine, you can actually run nearly everything that you would run on a Linux machine on Windows. And I know that because I'm running ISCE on my home computer right now. And it's a Windows computer.
Also runs on Mac OS. Since Mac OS is Unix.
People are asking about whether the talks are available on YouTube. You must not be looking on Slack because every day Melissa posts saying, here are the videos for yesterday. So yes, they are.
They're also on Moodle.
They're also linked on Moodle. In fact, that's where the messages that Melissa posts point you to. They're also on the syllabus document. So you have lots of places you can go and find them, and also the videos from the office hours. There's all this recorded material for your review.
And the lectures stay on YouTube forever. Well, I guess as long as YouTube exists.
Yeah, you can find us saying sometimes the same things and sometimes different things in other years on YouTube if you want to go dig down that rabbit hole. Okay. Any more questions can wait for office hours. We are out over time. So see you later, either at office hours at 5 p.m. Pacific or tomorrow morning at office hours, or the start of the live session at 10 Pacific tomorrow. Bye, everyone.